Good morning, everybody. Welcome to the last day of summer school. There we go. I wanted to welcome you to the last day where we're going to talk about uncertainty quantification from a wide variety of angles. It's going to be really, really awesome. We have a huge number of speakers today, and I want to thank all of them. They're going to introduce themselves since there's so many of them, unlike yesterday where we just had a small number, they're going to introduce themselves as they speak. I also wanted to thank Kathy Haynes, who is not speaking today, but helped contribute to the slides and the notebooks today. Next slide. So the goals today is to work on learning about uncertainty life cycle in the environmental sciences and AI development, and learn about common methods for uncertainty quantification and metrics to evaluate uncertainty. We all know that the AI method is not perfect. We need to be able to understand how certain and uncertain we are about the results and how much we trust them. And learn about different strategies for communicating the uncertainty, and especially how we communicate that uncertainty to a different set of audiences, because I think that the audience's needs matter in what we're going to do. This has truly been an interdisciplinary effort in putting this all together, all 4 days, but definitely today, and I'm looking forward to it, I hope, as much as you are. Next slide. So I think with this slide, this just gives you the outline of what's happening today. And we have, unlike yesterday where we did one long break, we're going to have 2 shorter breaks today. And I think I turn it over to Chris or Emma right now. I'm not sure.
That's me. So for part 1, we'll kick off the uncertainty quantification for machine learning with a few activities like we've done in the days past. So a couple of warm-ups to get everyone ready and in the lecture and Slido mindset. First one we're going to start with is, in your own words, tell us one thing you learned about selecting case studies yesterday. So building on part 2 of the day 3 lecture, what did you learn about case studies? How should you pick them? So I'll stop sharing so you can see those answers come on in. It's an easy one to get the Slido juices rolling, because we have a lot of people poised and ready to take on your questions in Slido. So as you have them, feel free to drop them in. Yeah, pick case studies that your users need and want. Exactly. So making sure you're working with the user and focusing on those needs, that's perfect. Okay, they should be chosen deliberately based on what you're trying to communicate to users. Yes, good hits and breaks. So knowing when it fails is great. Representative of the event has to be interest to the user. Exactly. Should be geographically relevant. Yeah, so a lot of those problems that Amy put out yesterday were not good spatial coverage of things. So it's great. Looking at the extremes, make sure you target your audience. This is awesome. Pick the case studies based on priority to the end users. This makes me so happy. The very user-centric answers right now. It's awesome. People are really listening. So establish a platform where you can get feedback from users and developing something that meets their needs. That's great. Is the most funneled towards the end users. Yep. Okay. So good theme. I'm loving this. It's seeing that we're really focusing on the end user for sure is really awesome. Yeah, and showing kind of the hard events or the edge cases can be helpful too, just to make sure you're really transparent about where this works and where it doesn't work. It can be really, really great. All right. Would have adversarial data for sure. And we got a lot to cover, so I'm going to cut this one off and we're going to move to the another one so that people have got things freshed up and they're ready to participate. What was your favorite part of yesterday's lecture? We're going to switch over to that one, poll 4.2. So we got sounds like people were paying attention yesterday. And what did you like? What was great? What resonated with you? Let those come on in at the same point. What was good about yesterday? Case studies. Yeah, sounds pretty fun. Walk through those, how to pick them. And it sounds like you all know how to pick them too. Focus on users. Yep, case studies again is a key part. What else is good from yesterday? Twitter examples. Yeah, so pulling from Amy's list there. FogNet example. Okay, great. Well, we're going to actually touch back to FogNet in a different way at the end of this one. So stay tuned. That's great. Discussing data. Yep. Talking with end users. R&R. Okay, nice. Selecting case studies, rare events. Okay. Discussing the data. Okay, cool. Seems like people were interested in these things. I think with that, we'll make sure we have enough time to get on. So I'm going to actually hop us to our next warm-up activity. And this is where I'm going to set the stage a little bit. Yeah, so perfect. We're going to opening for this discussion and we're building on yesterday's lecture. So what we're doing is we're thinking about this process, this big box where, our decisions across this entire system from, how data is collected, the quality of it, all these things through to the model output and the user relationship really impact the trustworthiness and the perception of trustworthiness for this end user. And so this question was kind of teed up yesterday. It's like, so how do we deal with uncertainty here? Which is, I think, a really big open question. And so I want to think about, we know there's room for, error and bias in this process, but where is there room for uncertainty? What part of this process are we going to see uncertainty, and what types of uncertainty throughout the development process? So where do we see this uncertainty come in? All right, range and quality. Okay, so thinking about probably more the data side of those. Aiml model isn't perfect ever. Yep, so that's the quote that Amy shared yesterday. It's not ever going to be perfect. We know there's uncertainty in the models that we're doing. So the model just doesn't perform well, or it's maybe not designed well. And then we have inconsistent results, uncertainty in the future too. So yeah, it's hard to forecast things perfectly when we're not sure how they're going to go. Everywhere, a human or nature play the role. So model uncertainty, observational, bias uncertainty, variance uncertainty, quality input data, judging reports accuracy, coming to calibration, limitations with the data or model. Excellent. So pretty much everywhere is where we're seeing data quality and selection, decision-making models, and predictive intervals. Okay, this is great. So how your case studies, kind of your case category is selected, the sign versus magnitude shifts, data model parameters. These are awesome. Hopefully we're going to touch on a fair amount of these. It's setting the stage pretty well. So from the data, from the model, extreme future events, not relevant to the past data. Okay, yeah, so making it hard to look from the data we have to the data that we haven't yet collected, the things we haven't yet seen. Data model not being representative, or like not having representative data, the verification, capture variability of the phenomenon. Yeah, or just uncertainty in the atmosphere. So the system we're working with is uncertain for sure. The process uncertainty along with the data and parameters. Okay, this is great. I feel like you're all pretty warmed up now. And so I'm actually going to skip the next question because these are great. You're hitting on all the right ideas and I think you're active and ready. So I'm going to actually hand it over to Emma to outline what we're going to cover today, give us a little overview.
Okay, sorry, need to skip through those slides. We are right here. Okay, so we have 3 parts today. As you saw, this is just an overview of the first 2 parts that both relate directly to uncertainty quantification, and the last part is more risk communication. So the first 2 parts, we have first the motivation and examples. Then we have different types of classifications of uncertainty. And then big topic, evaluation criteria for uncertainty estimate. And that's where you try to answer the question, what makes a good uncertainty estimate? Like once you get an uncertainty estimate, how can you test whether it's actually a good uncertainty estimate? And then we take a break. That's part 1. And then part 2 is discussing selected methods for actually generating uncertainty quantification estimation in machine learning algorithms. So that answers the question, how do you quantify uncertainty in machine learning? How do you do that? Okay, so just some motivation. Why do we want uncertainty estimates for our machine learning models? I mean, the first one is pretty obvious. We've been talking about this the whole week. We want to know how much we can trust the machine learning method's answer for a specific sample. I feed in a sample in operational use. I want to be able to say, oh, should I trust this or not? And if the machine learning model can tell me by itself whether it's certain or not so certain, that can be very helpful, for example, for a forecaster or for the general public. A nice side effect is that many machine learning methods, once you teach them to estimate their own uncertainty, that they also often give better predictions. So double purpose. And then thirdly, we want to know whether we can improve the model. So in the development stage, you want to see which kind of types of uncertainty you want to have. You have here aleatory versus epistemic because it tells you more about whether you can actually reduce that uncertainty or not through better models. All right. So just a very, very simple example from a very basic paper. So let's say you have a deterministic neural network and you're feeding in just one number and you get out one number. What it will give you is, again, you feed in, say, 5.8, outcome 6.0. But I have no idea when I run this operational, and I don't know, actually, other way around, the actual 6.0, sorry, too early this morning, too long a night, starting over. So in this case, you're feeding in a number and out comes a single scalar. And in this case, the actual number might be 6 and the predicted number might be 5.8. But since you don't know what the actual one is in operation, you really don't know how much to trust the 5.8. So in this case, it tells you 6.3, but the actual is 8.0. So you have no idea should you trust the 6.3 or not. But if we go ahead and we also do an uncertainty estimate, it can tell us, for example, estimate its own standard deviation for these cases, for the sample. So then the output would be not just the mean, so not just the mean of the prediction, but also the standard deviation. So it can tell you much more about how much to trust this. With that, I will just hand it over to Douglas.
Thanks, Aiml. So I'm gonna try to use this example to talk about the importance and motivation of doing uncertainty and also uncertainty propagation, just because we want to emphasize the importance of uncertainty and the uncertainty throughout the entire workflow. And here I'm going to use an example that I'm familiar with, which is the satellite climate data records. So the CDR is not for the carbon removal. This is for satellite climate data records. And a very classic example is for the sea surface temperature, which has been used a lot in the climate analysis. And because the sea surface temperature is a really key component of climate and the Earth's systems, so people are looking at how we can better quantify the uncertainty of the sea surface temperature for use for climate studies. And this is a table outlining all different requirements from different international coordination groups, such as the World Climate Research Program and the other ocean-focused international coordination bodies. As you can see, they have a specific requirement about uncertainty at global and at different levels for thresholds and for the horizontal resolutions to specifying what's the ideal sea surface temperature products for climate studies. If you can go to next slide. And when we are talking about the uncertainty of satellite climate data records, and here in the European Space Agency, they I really like their method about soliciting to getting the user requirements about the uncertainty. And there are different aspects of uncertainty and looking at how those uncertainty can be used. And more than 90% of survey users in the most recent sea surface temperature climate change initiative user requirements have preferred to have uncertainty estimates with sea surface temperature for their applications. And if you want, you can go to the specific reports linked on the slides. If you can go to the next slide, please. And so why we care about uncertainty in the climate monitoring? So in climate monitoring, we're often talking about the trend a lot of times about how the trend, how the climate has changed using a linear trend or other way of quantifying the trend. And using this example on the figure that we have multiple data points across the time. For example, this measure the sea surface temperature and for the past 10 years. And the arrow bar here indicating the uncertainty of each individual measurements. And when we're doing the estimation of the trend, oftentimes that we're doing linear linear regression. And because of the uncertainty, that's the trend estimation can be influenced by the uncertainty of the observations, depending on the error of each individual time steps. So thinking about it as a noise to signal ratio. If you go to next slide. So ideally, when we have a perfect value of the observations for the climate monitoring or the trend analysis, which is outlined in this orange line, and then we also have the best data observation, so lowest uncertainty. And then on the blue line, which is the less accurate data, so which means the observation of the sea surface temperature has higher uncertainty. And when we are trying to looking at the same trend uncertainty or the same confidence in the trend estimation in this, and we can see that the observational data length will be much longer if you try to get the same confidence in the trend. Just because think about it in a way that if you have more noise in your data, then when you try to estimate your trend, you need longer time series to really figure out the trend that you can trust in. So because the climate change, the trend oftentimes the signal can be small. It's, for example, we're talking about 0.2 degree in a decade, and then if your observational data or the satellites sea temperature are have higher uncertainty, then the trend estimation can really require much longer time series to detect that signal. If you go to next slides, please. And going back to how we generate the sea surface temperature or the satellite product overall in the workflow, it sometimes can look like a maze when you're going to the product description of those, how the methods developed. But overall, you look at from the top left, which is the starting points for the satellite product generation workflow, and to the end, which is like bottom right, and that is the end point is usually when the users are accessing or using this data. So that can be like gap field, the gridded sea surface temperature for a climate analysis. And but starting point is a satellite radiance or satellite imagery, the raw data. And so the satellite data retrieval often requires a series of transformation from the raw signal to the digital to the physical parameters, and then to gridded and then gap field products that oftentimes users start to use. And so that the whole workflow can be prone to the uncertainty in each step. So the uncertainty can propagate through the entire workflow. And if you go to next slide, please. And so here is just an overall simplification of how an entire workflow of satellite products from the very raw data that's a level 0, so oftentimes, and then to the level 4, a higher level, which is gap field that user often use gridded data sets. So if you go through each steps from level 0, the raw data, that there are certain factors may cause uncertainty in the data. For example, the digitization of the data and then the noise in the sensor data themselves and the failure of certain instruments that happens more often than you think, because satellite sensors can be fragile and in the space that oftentimes you have those failures in the instruments. And that's the potential error source in the for level 0. And for the level 1B or in the satellite world, that level 1B is oftentimes the radiance data. So from level 0 to level 1B, that you have the calibration for the sensors, and then there are also geolocations of those for this individual pixels within a satellite image that can also have errors in the workflow. And next slide, not the next slide, yeah, not quite there yet. Sorry. So level 2, that we have the granular data, which is from the radiance. Then we have an algorithm trying to retrieve the physical parameters. So that have the algorithm accuracy, the definition of the variables, and dependency on the data. So that's the error source. And then go to the level 3, which is the gridded data, basically, that we have the granules that very instantaneous observations. We're trying to create them into a global map, the spatial that requires some spatial temporal sampling from those granular data. And there's also error coming from the locally correlated data. For example, that you have certain atmospheric phenomena that is happen in geographical regions. So that phenomena may cause errors, and then it's locally correlated. It's not individually based for each pixel. And for satellite data, sometimes you have gaps in the data themselves because of the coverage of the sensors or the contamination of the cloud and other aspects. And then which you will generate the gap field data from the level 3. So using interpolation or post-processing methods to get those like highest level gap field satellite data. And so that from level 2 to level 4 are most common stage for the machine learning use cases in a lot of satellite applications. So the errors in each processing steps in the workflow will propagate through the workflow and sometimes being amplified even to the desired products information. And sometimes it can be reduced. For example, in the gridded data, that when you're doing the aerial average, that you might reduce the noise in those individual pixels, so that can reduce certain like noise uncertainty in it. So if you can go to the next slides. And when we are talking about how the uncertainty may affect different aspects of uncertainty goes into the analysis workflow overall, then the scale and different applications matters as well. So here again is from the European Space Agency's sea temperature group that they are looking at how different spatial resolution and different temporal resolution of the analysis, the uncertainty may matter in different cases. So at the very instantaneous and 1 kilometer high resolution analysis, that contribution of the uncertainty mostly coming from those random errors from the sensors and from the from other aspects, and those locally cause like errors. But if you move on to those like higher dimension or the coarser resolution, both in space and time, you're looking at decadal phenomena in there. It becomes more those systematic errors in the data set. For example, in the satellite case of sea temperature, which is because of the bias in the sensors or the instability of different satellite platforms that can cause aerosols in this analysis. So that application context can be very important for the uncertainty quantification and understanding uncertainty for the applications. If you go to the next slides, please. And so now I always want to go back to the uncertainty, the mathematical equation when we're talking about uncertainty. So assuming that our target y is a function of multiple predictants. For example, in the machine learning models, you have multiple input variables, input features into a model. That y is a function of x1 to xn. And then the overall uncertainty can be the combinations of errors from each individual predictants and while taking account of the correlated errors among different predictants. For example, there are certain errors can be spatially correlated or temporally correlated or sometimes physically correlated, depending on each individual components of this model you are creating. So overall uncertainty can be, oftentimes we assume them are independent, but in the reality, those errors can be correlated. So we need to be careful when calculating the uncertainty in a mathematical way. We want to account for the correlated errors there as well. If you go to the next slide. Maybe you have been asking why we're talking about uncertainty in satellites, and I just want to bring it back to machine learning and AI cases and why the uncertainty propagation matters. So going back to the workflow that we have been always referring to since the day one, that we have the entire AI workflow is from data to data processing to model development, output, and then users. And in the entire workflow, there are different parts of the uncertainty may occur. For example, the uncertainty in the input data themselves, from satellite, from observation, from simulation that we have talked about yesterday. And then there's also uncertainty in the data processing steps. How you process your data may introduce additional errors in it. For example, you're doing the average across certain regions, and then that will create there's certain like spatially correlated errors may be reduced or like even increase amplified. And then when you're assessing your model, there's uncertainty in the testing data. So this can create additional layer of uncertainty. And then again, you have the uncertainty in the trained machine learning AI models, which will be a focus on the methods we're going to talk about later on of different methods of how you quantify the uncertainty in the trained AI machine learning models. And I'm not pretending I'm the experts in the risk communication, but then there's another layer of how you communicating the uncertainty in the with the users and the communicating the risk. So that will be covered by Anne and Chris later on in the lecture today. If you go to the next slide. I think, yeah, we just want to take a quick break and to give you some time to ask any questions if you have any. but I will ask Chris or somebody else who are monitoring the Slido to see if there's any questions there.
Not right now. So there's a few that they've been responded to.
Okay.
So it looks like we're actually doing pretty well.
Great.
Just give it another second. Looks like we just had one pop in. What are use cases in AI ML? Well, we're going to talk about two cases, so that tees up our next question really well. So we'll give a few of those in just a second. If you can hold on to that question. So we're going to talk about two specific cases in that one specifically. So it looks like we don't have any other Slido questions coming in, so we can maybe just introduce those questions now while you're thinking. And so two case studies, here's some ways to think about this more concretely, because Douglas just beautifully set up, okay, let's refocus back in on this AI and ML situation and context. We're providing two different examples from TAI4ES, so that are part of the collaborations with researchers on this really great interdisciplinary team. So the first one's cold stunning predictions. The second one is estimating precipitation from satellite imagery. And I'm going to give a quick overview of the cold stunning prediction. So if you hit the next slide, this is a model that comes out of Texas A&M Corpus Christi. So for the people who were enjoying FogNet yesterday, it's from the same great team. So Philippe Tissot and all his great collaborators like Scott King, and it also involves collaborators from IBM and other TAI4ES people who are hopefully watching the chat for you and can answer any more specific questions. But I just want to give a brief overview because we're going to talk about this model a couple of different times throughout the lecture as a good example of the importance of uncertainty from all these different examples, or kind of these different angles like Douglas was just talking about. And so the goal of the model is to essentially be able to predict water temperatures, so below 8 degrees Celsius for about 24 hours, because these events lead to cold stunnings for turtles. And so they're using a shallow neural net to predict this. And we're working with stakeholders on these things to make sure they can communicate about when we need to essentially stop traffic in this, this area so that sea turtles kind of have a safe space and we can work on these different points. And so this model has really important impacts because it's communicating with stakeholders pretty collaboratively across a bunch of different ranges of understanding of AI, but also has different uncertainties, because you're still forecasting into the future. Will it really actually get to the temperature that's going to be important for that threshold? So you see like those red lines, is it going to dip below or not, and when, and for how long? So it's a lot of different questions that have uncertainty around them, being able to communicate that with the stakeholders. And so you kind of have these questions, and I'm not going to actually ask you these now, but we will later, is when you're working with a stakeholder, how do you best quantify, visualize, and communicate this uncertainty? So we don't know exactly what the temperature will be, but we're doing our best to predict it. We don't know how long it will be, a certain run of temperature, but we still have to make a decision, and we still need to communicate that ahead of time to our end users. And then co-production of the models with stakeholders. How can we do that? How can we make sure we're really engaging our users and meeting their needs? Do they want us to be a little bit more conservative and just err on the side of more time off, or is more time, not running this traffic through this port very expensive? So they want to be, really sure that if they close it, it really, really matters. So this is one example that Ann Bostrom will come back to in the second half and really dig into and show us how we're communicating uncertainty in many of these different ways. And the second one I'll pass back to Emma to describe.
All right. And for the second one, I want to be very clear because I think Chris said that this is part of our TAI4ES collaboration. It is in a way because we're trying to do the same as what these people are doing, but this is not our work. This is work by Marco Oreskinen and his group. So this is about this paper that you see here at the top. And the task is to classify precipitation type, whether it's stratiform or convective, based on passive microwave imagery. And so the goal is to provide two outputs: the map of precipitation type, so that's just a prediction, it indicates stratiform or convective per pixel, but also a map of uncertainty that again indicates how much to trust the classification per pixel that's provided by the neural network. And the method they use is the Bayesian neural network. And we will go into more details for this approach later. I just want to show you what this could look like. So here's an example. And again, that's the same paper by Oreskinen et al. So you have that in panel B, so the second from the left, you actually see the ground truth that is from dual polar radar. And so here you actually see a classification: blue is stratiform and red is convective. This is what you want to get. On the left in panel A, you see the current operational algorithm, and you can see that it's doing okay, but it's not doing great because it really misclassifies a lot of things as convective that really are stratiform. So then you see on the left, the two left panels, C and D, they show the output of their Bayesian neural network. And you first see the prediction, and you can already see panel C is much closer to panel B. And also, if you closely look, for example, down here, or I don't know whether you can see my mouse, but in the lower part of this, there's a lot of uncertainty. As you can see, in panel D, you have yellow for uncertainty. So in the lower part of the image, you have a lot of uncertainty, and that's indeed where the model gets a lot of the classification wrong. So it seems to be a good indication of this. And again, we will get back to that more later. I just wanted to show you one application of how you could use that when you process satellite imagery. All right, with that, we go to classifications of uncertainty. So the key point I want to get across is that there are many, many different ways to classify uncertainty. And the different classifications arise from two different things. Number one, the needs of the specific application and of the end user. And number two, the information that's available and the approaches used to develop uncertainty estimates. So when you start reading papers, it can be very confusing to encounter all these different classifications, because almost every paper you see a different application, different classification. And you just think, oh, I got it now. And then you get to the next paper and it's all different. So don't be surprised to see those. It's not you, it's the nature of the field. Almost every application will have a different classification. For example, if you have two approaches that use very different, if you have two different approaches use very different classifications, such as the following ones. If you use a component-based approach, you're modeling uncertainty of each component separately, often based on expert knowledge, and then you propagate the contributions. In that case, you're probably going to have a classification that's based on different components. However, in the typical AI approach, you're only given a data set and an AI model. So you have no information about components, so your classification has to be very different. And in fact, we're first going to look at the typical classification of uncertainty in AI. And I know there were some questions later whether we get into reducible and irreducible. That's exactly what this slide is about. So the key classification, aleatory uncertainty, is a natural randomness in the underlying process. It's also known as statistical, stochastic, or irreducible uncertainty. Classic example, you're tossing a perfect coin. You just cannot predict, no matter how well you know the model, there's just a stochasticity in there that you don't know whether it's this or that. So even the best deterministic model of the system cannot predict the outcome of tossing a coin, because the process that you're modeling has stochastic properties. So this part is irreducible. This uncertainty can be estimated, but it can't be eliminated. Then there's epistemic uncertainty, which is a scientific uncertainty due to limited data and knowledge. That's also known as systemic, model, or reducible uncertainty. And this one is based on our ignorance. We just don't know the system in a state well enough. So if you go back to the coin, let's say somebody's tossing a coin, but the person has two different coins. One coin has only tail on both sides, and the other coin only has head on both sides. And they're tossing it 100 times the same coin. Well, it's going to be the same result every time, but because you didn't know which coin the person had, you don't know what the output is going to be. So that would be an example of epistemic uncertainty. Classic example, training a machine learning model with few data samples. That includes epistemic uncertainty because you just don't know enough from your observations about the underlying process. This uncertainty in theory can be reduced by feeding more appropriate data and or by adding more physical knowledge. In practice, you still can't get rid of all of it, clearly. You will never know the system perfectly. So this part is in theory reducible, but in practice, only part of it is reducible. While the first part, the aleatory, is just completely irreducible. Just giving you a quick example. Here's distribution of training data. The blue dots are training data. And what I've done here is I basically had y of x is non-distributed for all x in the whole range. And your mean value for your distribution mu is just sine of x times pi. And then I have a standard deviation of 0.1 times sine of x times pi. That represents the internal variability of the data here. So that's the stochastic part. I also threw in different sampling. So on the left side, we have in X a high sampling rate. So you have lots of blue dots here. And here we have a very low sampling rate, so low density in X. Okay. What does it do in terms of uncertainty? Well, if I now just fit a neural network model through this, a very simple one, what do we notice? And we notice it kind of gets the mean over here where I have lots of data. And then here it just goes off because it doesn't have enough data points. So what you see is the classic two types of primary types of uncertainty. The ones on the left here that come just from the variability of the data, from the internal variability, that is your aleatory uncertainty. What you see on the right side over here is the very large epistemic uncertainty that comes simply from not having enough training samples. The neural network just in this case doesn't know what to do. So keep that in mind. Epistemic uncertainty really comes often from just having too few data samples, too few observations in a certain regime, while aleatory uncertainty comes from the internal variability. There's nothing you can do about it. Right? Okay. And if possible, you want to know both. So do your uncertainty quantification methods capture both? Well, different methods capture different types of uncertainty. In theory, the non-Bayesian methods capture only the aleatory, the irreducible uncertainty. In theory, Bayesian methods can capture epistemic uncertainty. And in theory, some combinations of methods can capture both. But in practice, what the various methods capture is yet totally another question altogether. Some of them are much better than others. Some are really good at capturing epistemic or aleatory, and some are not so good. So the estimates vary greatly between the different methods. So once you use a method, you then really have to make sure you have to have evaluation criteria for uncertainty estimates, and they're really, really important. You can't just use through one of those uncertainty quantification methods at your problem and expect, oh, I'm getting a number, it must be right for your uncertainty. So the next big topic is how to evaluate these things. And with that, I will skip over this one just in the interest of time. So we will ignore the Slido prompt as well, and we will just go straight ahead with a quick break, checking in Slido. Are there any big questions in Slido? Chris, did you see anything?
There are a few questions, but Maria and everyone else is really on top of them. Nothing has not been responded to. So everything is covered so far. But I don't know if Maria, if there's any you want to throw out to the full crew, let us know.
No, I think we just had a lot of questions about aleatory versus epistemic uncertainty. Hopefully people feel at least a little bit clearer on those. And if not, it's confusing. So
it is confusing, especially I should point out, there's aleatory and epistemic uncertainty in the data, but then it propagates through and your machine learning model has additional epistemic uncertainty. So it's not a trivial thing. This stuff is hard. This stuff is tricky. So with that, we will turn it over to Ryan. And maybe, Ryan, you can introduce yourself because you haven't spoken yet this week.
Sure, I'm Ryan Lagerquist. I'm a research scientist at CIRA and also NOAA GSL. So I work for both institutions at the same time. And I've been doing machine learning applications to weather prediction for about 10 years now. So starting in undergrad with Environment Canada, and I went to University of Oklahoma for my master's and PhD and studied under Amy McGovern. And I also had a Google internship along the way. So yeah, lots of experience applying machine learning to different types of weather prediction tasks and different theoretical stuff as well. And this is one of the theoretical things I'm working on right now is uncertainty quantification. Is that a good enough introduction, Emma? Should I have said something more?
That's perfect.
Okay, great. So this section 3 will be on evaluating uncertainty estimates. So if you have a machine learning model or really just any model that provides you estimates of its own uncertainty, you need to know how good those estimates are. And it's kind of a tricky thing at first glance, thinking about taking an uncertainty estimate and then figuring out if the uncertainty estimate is right, because where's your ground truth? How uncertain should you be? How much uncertainty is too much? How much uncertainty is too little, et cetera, et cetera. So that's what this section is going to go over. and hopefully you'll get a better grasp for how to figure out if your uncertainty estimates are good. So in this section, I'm going to talk about 5 different evaluation tools. Actually, I'm going to talk about the first 4, and Marie McGraw is going to talk about the last one. So we'll go over first the reliability curve and attributes diagram, the spread skill plot, the PIT, which is the probability integral transform, the discard test, and then the continuous rank probability score, the CRPS. So next slide, please. So this slide here is on the reliability curve and attributes diagram. So I'm going to start by talking about the reliability curve. So the thing you're seeing on the right-hand side of this slide is just a reliability curve, and I'm going to ease you into it. So don't worry if you don't get everything on this slide. That figure is going to pop up again, and I'll explain what's going on in that figure. And then the attributes diagram is basically just a fancy reliability curve with extra reference lines and stuff in the background. So these are kind of the same thing. One is just an advanced version of the other. So I'll start off by saying the reliability curve is typically used to evaluate probabilistic predictions, and it's typically used for binary classification where you have to predict a yes or no event. So yes or no, is there going to be cold stunning? Yes or no, is there going to be convection? Yes or no, is there going to be a tornado, etc. But reliability curves can also, they can be modified for multi-class classification. If you, for each class, if you do a one versus all approach, we're not going to talk about that today in any more detail than what I just said. But reliability curves also can be modified for regression where you're predicting a continuous real number. And that I will show later. So reliability curves evaluate only the central prediction of the model and not the uncertainty. So for example, if you have a model that's predicting tornado probabilities, and if it gives you a set of 1,000 probabilities for every single storm, to create the reliability curve, you're just going to take the mean of those 1,000 probabilities. So that's going to be your central prediction. Reliability curves don't have anything to do with uncertainty estimates, which kind of begs the question, why are we talking about them here in this lecture on uncertainty? And the reason is, in studies involving uncertainty quantification, people very, very often use reliability curves to evaluate the central prediction, and then they use other stuff to evaluate the uncertainty estimates. So next slide, please. So one big caveat here, reliability curves are used even if the model's not truly probabilistic. So most machine learning models, I don't know if this has been covered this week in the summer school or not, but most machine learning models that do classification output confidence scores, or you can call them pseudo probabilities. I think I misspelled pseudo, whatever. So most of these models output confidence scores, which are pseudo probabilities. They're not truly calibrated probabilities. So this is the kind of thing where we get away with colloquially calling them probabilities, but a statistician would get upset with someone calling the raw output from a machine learning model a probability. So yeah, like I said, we just call these things probabilities, and then we use the reliability curve to evaluate how calibrated these probabilities are. There's nothing wrong with using the reliability curve for this purpose, as long as you understand the difference, as long as you know that you're evaluating pseudo probabilities and not true probabilities. So that's the big take home point of this slide that's boxed out in red at the bottom. And next slide, please. So going back to this figure that I showed you, now I'll explain what's in this figure. So the reliability curve plots predicted event probability versus conditional event frequency. So it's answering the question that's outlined at the bottom of this slide. Given a predicted probability P, how likely is the event to actually occur? So if you're forecasting tornadoes, or you have a system that forecasts tornadoes, people who are using that system, the end users, the meteorologists, they're going to want to know for each forecast probability, what's the likelihood of there actually being a tornado? And ideally, this plot follows the one-to-one line. So for example, if you have, if one of the points in this curve is at 0.4, that means in cases where you forecast a 40% probability of tornado, the tornado actually happens 40% of the time. But this sigmoid shape is often what reliability curves look like if you don't do any sort of calibration. If you just take the raw output from a machine learning model, you often get this sigmoid problem. So for example, if you look at this point that I'm mousing around here, this is saying when the forecast probability is 35%, the conditional event frequency is only like 5. So if you're forecasting tornadoes, what this is saying is in the cases where the system forecasts a 35% tornado probability, tornadoes actually only occur 5% of the time. And then if you look at one of the points up here on the other side of the sigmoid, this point that I'm mousing around is saying in cases where the system forecasts a 65% tornado probability, tornadoes actually occur 95% of the time. So you're, other than this point that goes through the one-to-one line in the middle at 0.5, this model is very miscalibrated. I'm going to skip the second bullet point here, talking about how reliability curves are created. Basically, you bin all your data, but we won't go into that today. So what else did I want to say? Next slide, please. There we go. That's the stuff I wanted to say. So ideally, the conditional event frequency should always equal the forecast probability, which means you should be following the one-to-one line. And that's the dashed gray line here. So this, you can call this the one-to-one line, or you can call it the perfect reliability line, whatever you prefer. At points below the gray line, the model's predicted probability is too high, so you say the model is overconfident. And at points above the gray line, the model's predicted probability is too low, so you say the model's underconfident. So at lower forecast probabilities here, the model is overconfident, and at higher forecast probabilities, the model is underconfident. And this is a typical problem you see in machine learning. So next slide, please. Okay, so now we're going from a reliability curve to an attributes diagram. So like I said, to get an attributes diagram from a reliability curve, you just add stuff. You add a couple more reference lines, and you add this histogram, and you add this shaded area, this polygon thing. So the diagonal gray line is still the one-to-one line, or the perfect reliability line as before. The vertical gray line is climatology. That's the event frequency over the entire data set. So here the climatology is about 10%. The horizontal gray line is the no resolution line, and the blue shaded area is the positive skill area. So I'll try to go over this in a way that's sort of intuitive. So a model that has no resolution follows the no resolution line, which is this horizontal line. So if you, yeah, I keep forgetting no one can see my cursor. They can only see Ema's cursor. That was a bit silly. And so this blue horizontal line near the bottom is the no resolution line. So if you had a model that was completely uninformative, it would follow the no resolution line. So regardless of the forecast probability, no, it's the gray line near the bottom, Ema, the one that's completely horizontal. Thank you. Yeah. So for a model that's completely uninformative, your reliability curve would follow the no resolution line. It would just be this horizontal flat line, which is saying regardless of the model's forecast probability, the expected event frequency is the same. So in this case, with the horizontal line being around 0.1, if your reliability curve followed that line, it would be saying, regardless of what the model says, expect tornadoes 10% of the time, whether its forecast probability is 0 or 100 or anything in between. So that's a really bad model, completely uninformative. A climatological model, one where the predicted probability is always just the event frequency over the entire data set, has a reliability curve with only one point. It's at the intersection of the climatology and no resolution lines. So in this case, it would be at 0.1. And when I say positive skill, that means the Breyer skill score is greater than 0, or the Breyer score is better than always predicting climatology. And that's any time your reliability, or any point where your reliability curve is inside this blue shaded area, that's a point where you have positive skill. So you're doing a better Breyer score than climatology. And then the histogram just shows how often each probability is forecast. Next slide, please. So I think in the interest of time, I'm not going to dwell on this slide too much. Really, the main point is highlighted at the top, and it's that the attributes diagram can also be adapted for regression problems. So here, instead of the x-axis being a forecast probability and the y-axis being a conditional event frequency, in this case, the x-axis is a predicted real value in watts per square meter. We're predicting a radiate of flux. This is from a project that I've actually done. So this is a real attributes diagram. So on the x-axis is a predicted value for net flux, and on the y-axis is the conditional mean observation for net flux. And here, the reliability curve looks really, really good. So every point is on the one-to-one lines. This is saying when the model forecasts a net flux of -200 watts per square meter, you expect the actual net flux to be minus 200 watts per square meter. When it predicts 500, you expect the actual value to be 500, etc. Next slide, please. Great. So now we're on to stuff that actually deals with uncertainty. So we're now going to talk about evaluation tools just for uncertainty estimates. So the first is called the spread skill plot. This is similar to the reliability curve, but it may be used only for models that include uncertainty. And the spread skill plot can be used for classification models or regression models. So if you look at, I'll start with this example on the top right. You can ignore the example on the bottom right for now. So in this example on the top right, the x-axis is the model's predicted spread. So it's the standard deviation of the predictive distribution. And the y-axis is the model's skill. It's the root mean squared error of the mean prediction. And each point in the spread scale plot corresponds to one bin of spread values. So again, you bin all your data to create a spread scale plot similar to what you do for a reliability curve. So the spread scale plot answers this question outlined in the box. Given the predicted model spread, what is the model error? Next slide, please. So for a model with perfectly calibrated uncertainty estimates, the spread always equals the skill. Or in other words, the standard deviation of the predictive distribution always equals the root mean squared error of the mean prediction, or standard deviation equals standard error if you want to use an even different set of terminology. So a perfect spread scale plot follows this dashed diagonal line. At points below the one-to-one line, in the top plot, there are really none of them, but in the bottom plot, there are. So I'll go back to these plots for a second. The top plot is a spread scale plot for a classification problem, and the bottom one is a spread scale plot for a regression problem, where in this case, someone is predicting a temperature in kelvins. So if you look at the bottom plot, most of this curve is below the one-to-one line. When you're below the one-to-one line, that means the model spread is greater than the model error, or in other words, the model is overspread or it's underconfident. And then if you look at the top plot, the spread skill, the curve, the orange curve, is above the one-to-one line basically everywhere. And at those points above the one-to-one line, spread is, the model spread is less than the model error, so the model is not spread enough or it's overconfident. We've also included histograms here to show the number of cases in each spread bin, because often you have a very non-Gaussian distribution of predicted spread values. So for example, in the plot at the top, you'll see that the on the left side of the histogram is the only place where the bars are tall. So the vast majority of cases have a small predicted spread, and then you have a long right tail. And also the overall quality of the spread scale plot can be summarized by taking the mean distance from the one-to-one line. So if you take each of these points and calculate the distance from the one-to-one line and then average that, you get something, well, I kind of invented this term. I don't know if anyone else has used this, but you get something called the spread skill reliability. So when you see SSREL, like in the title of this top plot, that's what SSREL is. So next slide, please. All right, the next method is the PIT histogram, PIT being the probability integral transform. So on this slide, I'm not even going to talk about the histogram yet, because that part's easy to understand. I'm going to talk about what exactly the PIT is, because I think that's the harder thing to understand. So the definition, being a little jargony here with the first definition, and then I'll break it down. The jargony definition is the PIT is the value that the predictive CDF attains at the observed value. So the predictive CDF is the cumulative density function of all the predictions from the model, and then you only have one observed value. And to calculate the PIT, you find out where the observed value lies in that cumulative density function. An alternate definition, still being a little bit jargony, the PIT is the quantile that the observed value reaches in the distribution of all the predictions. So in this schematic on the right-hand side, I've tried to break it down for you. So the orange curve is the model's predictive distribution. So the y-axis here is probability density, and the x-axis here is just a forecast value. We could be forecasting who knows, wind speed, temperature. Well, I guess temperature can't be negative if it were in kelvins. Let's say we're forecasting U wind or something like that. So this orange curve is the predictive distribution for U wind. And then these dashed vertical lines in green are different observed values. And for different observed values, I've plotted the PIT next to them. So if you look at this, this vertical line on the left, which corresponds to a value of about -4, in that case, if the observed U wind was -4, that falls below the entire predictive distribution because no value in the predictive distribution is less than -2. So in that case, your PIT, your probability integral transform, would be 0 because your observed value is completely outside the predictive distribution and to the left of it. And if you look at this other extreme case on the right-hand side, where the observed value is 10, in this case, your observed value is completely outside the predictive distribution and above the predictive distribution. So in this case, the PIT is 1.0. And then if you look at the dashed line in the middle corresponding to a value of about 0, say your observed U wind value is 0, this is exactly the median of the predictive distribution. And in that case, where your observed value matches the median of the predictive distribution, your PIT is 0.5. And for the dashed line just to the right of it, where the PIT is 0.9, that means your observed value reaches the 90th percentile of the predictive distribution. So hopefully I've explained that sufficiently that people now understand what the PIT is. Next slide, please. So the PIT histogram now is just a histogram of all the PIT values. So if you have your validation data or your testing data, you're going to get a PIT value for every single observation. And then you can plot the histogram of all these PIT values. For a perfectly calibrated model, so one that has the best uncertainty estimates, the PIT histogram should be uniform. So these 10 bars or however many bars you decide to plot should all be the same height. You should just have a rectangle here. In this case that I'm showing from a paper by Libby Barnes et al., the PIT histogram has a hump in the middle. And when you have a hump in the middle, that means the model has too much spread, so the model is underconfident. Whereas if you have humps at the sides, so if you imagine the opposite of this histogram, imagine a U shape where you've got a really tall bar at the left-hand side and a really tall bar at the right-hand side, and then a dip in the middle. That means that the model has too little spread or is overconfident. So that's how you read the PIT histogram. Next slide, please. It looks like there's stuff in the chat for me to. Oh, I'll finish talking about the PIT histogram first, and then I'll address the stuff in the chat. So I don't want to spend too much time on this slide. Atmospheric scientists are usually more familiar with the rank histogram, which was invented by Talleyrand and discussed in this paper by Aiml. You can go there for more details. In any case, the PIT histogram is a generalization of the rank histogram. The rank histogram is used for ensembles, usually ensembles of NWP or physical models, where the ensemble contains a finite number of members and thus generates a finite number of predictions. Whereas the PIT histogram can be used for any method that generates a predictive distribution. So that distribution could be created by collecting deterministic predictions from each member of an ensemble, predicting the quantiles of a distribution, predicting the parameters of a distribution, like predicting the mean and standard deviation for a Gaussian, or really anything. And also I want to take this opportunity to note that every single evaluation tool I'm discussing in this section 3 can be used for any model that generates a predictive distribution. So it doesn't have to generate the distribution in a certain way. As long as you just get a predictive distribution, then you can use any of these evaluation methods to figure out how good the uncertainty estimates are. Unfortunately, the rank histogram and the PIT histogram can be interpreted in the exact same way. So everything I just said on the last slide about where a uniform histogram means the model is perfectly calibrated. If it's bunched up in the middle, the model is underconfident. If it's bunched up at the sides, the model is overconfident. Those things hold true for the rank histogram and the PIT histogram. So if you're an atmospheric scientist who's more familiar with the rank histogram, you can take everything you know about interpreting that plot and carry that over to PIT histograms. So next slide, please. And it seems like whatever question was lingering in the chat or the Slido, I've answered. So cool. So I'll get on to the next
Hey, Ryan,
method.
Right,
Yeah.
I will just say we're running a little late, but that's fine.
right.
So no,
Okay.
don't rush it because this is important stuff. So I'm just telling the audience, don't be concerned. We have some material later that we can skip. So we probably take the break a little later, but we'll make up for it later. So just keep going at your regular speed, Ryan.
Okay, thank you. So this next method is called the discard test. The discard test, it compares the model error versus the fraction of highest uncertainty cases discarded. So the idea is you've got a validation set or testing set with a bunch of cases, and you can compute the model error. First of all, you compute the model error on all the cases you have, and then let's say you discard the 5% of cases with highest uncertainty. When you do that, the model error should go down, because when you get rid of the high uncertainty cases, the cases with highest uncertainty should also have the highest model error. So when you get rid of, say, the 5% of cases with highest uncertainty, the model error should improve. If you then get rid of the 10% of highest uncertainty cases, and then 20, and then 30, and then 40 and 50, and you keep, if you sort your evaluation set from high uncertainty to low uncertainty, and then you keep getting rid of high uncertainty cases, the model error should continuously improve as you do that. So that's my verbal rendition of the procedure that I've put here in the bullet point. So for a model with well-calibrated uncertainty estimates, the error should decrease monotonically as the discard fraction increases. So every single time you increase the discard fraction, this line should go down and down and down and down. In this case, this is, again, for a real model that I trained. I believe I was forecasting the occurrence of convection, trying to figure out where thunderstorms are going to be in an hour from now. The model error, the metric that I used here, was cross entropy. So that's what's being plotted on the y-axis, and what's plotted on the x-axis is discard fraction. So for a model with perfectly calibrated uncertainty estimates, this line would always go down. You wouldn't see these little jumps up. So for this example, I've plotted the monotonicity fraction as 73.68%, which I think is the same as 14 out of 19. Because I have 20 different discard fractions, that means I increase the discard fraction 19 times, and 14 out of those 19 times the model error decreases, but sometimes it increases by a little bit because the uncertainty estimates are not perfectly calibrated. So next slide, please. This is just a mathematical definition of the monotonicity fraction. I don't think I need to go over this. I think the conceptual explanation is better. So next slide, please. And this next slide is Marie's. So.
And Marie, if you can introduce yourself first.
Yep. Hey everyone, I'm Marie. You may have seen me in Slack for the Trust Fund or answering questions on Slido, but now I'm here on video. I'm a postdoc at TAI4ES. Some of my projects include machine learning and tropical cyclone rapid intensification, understanding sort of data biases and trustworthiness, and then uncertainty quantification and machine learning, what we've been talking about today. And I just want to quickly remind everyone, the slides are linked below the video. You will have access to these slides after this talk. And I think in a few minutes, we will post some additional resources related to the content we've been going over today. So really, don't worry about getting all these equations memorized or anything like that. This is a lot of material. Mostly, we just want to sort of almost give you the tools so that you know what to kind of Google and what to think about in a big picture sense. And you can come back and relearn the details later, if that makes sense. Okay, so I am going to talk a bit about the continuous rank probability score, or CRPS. So CRPS is essentially a way to compare probabilistic predictions to deterministic predictions and or observations or truth, which is inherently deterministic. We only have one observation. So in weather forecasting, forecast centers will often run an ensemble of weather predictions, a probabilistic ensemble, where we perturb the initial conditions by very small amounts and see how that changes the forecast. And frequently we'll also run a deterministic best guess forecast, which is often a model run at higher resolution, but we only do that once. So it's nice to be able to kind of compare this probabilistic ensemble with our deterministic best guess and or our obs. So my favorite way to think about CRPS is visually, and we can think about it as a comparison of cumulative density functions or CDFs. So we want to see our the CDF for our OBS or a deterministic model is basically going to be a step function where we have 0 probability before our sort of truth occurs, and then we go immediately to 1 probability, so that step function. Whereas for a probabilistic prediction, we have that sort of smoother S-shaped CDF. So this figure here, you can see our truth is in blue, our probabilistic model is in orange, and our sort of best guess deterministic model is in green. So the CRPS is kind of that area between the model curves and the OBS curves, if that makes sense. Next slide, please. And then, yeah, so CRPS varies from 0 to infinity. The optimal value is 0. That would mean our 2 CDFs are on top of each other. There's no space between them. And we want that space between our 2 CDFs to be as small as possible. So this is just sort of the mathematical formula for CRPS here, but really the important thing to note is that it's actually really a probabilistic adaptation of the mean squared error. And if we have only one member in our ensemble, this CRPS function actually just kind of reduces to the mean squared error, mean absolute error, not mean squared error, big difference, mean absolute error. Next slide, please. So some of the advantages of CRPS. CRPS is something, if you're in the meteorology field, you've maybe already seen it, especially if you do numerical weather prediction. And CRPS considers the full probability density function, not just the mean or standard deviation or certain quantiles, like your 5th or 95th percentile. The CRPS can be used as a loss function to train neural networks, which we will talk about later this morning. And basically what that looks like is we create an ensemble of predictions and use that to quantify uncertainty. And the ensemble members are trained to represent the probability density function and don't require any information about the distribution a priori, which is nice. And we've just listed a couple of the sort of canonical references using the CRPS, which derive the CRPS and sort of show you the math and how we use it in meteorology. So I think with that, if we go to the next slide, I think I'm going to hand it back to Ryan to give the overview.
Thanks, Marie. So this is just to summarize all the evaluation methods we talked about in this section. So for each method, I'm going to tell you whether it can be used for regression models, whether it can be used for classification models, and then what the method tells us. So method number 1 is the reliability curve or the attributes diagram. Those can be used for both classification or regression, but big caveat here in the red, these things evaluate only the central prediction and not the uncertainty estimates. For classification, what the attributes diagram tells us is the observed event frequency as a function of the predicted event probability. And you can also get the Breyer score and the Breyer skill score out of the attributes diagram, recalling that that blue area is where your Breyer skill score is positive. An attributes diagram for regression tells us the mean observed target value as a function of the predicted target value. So for example, the mean observed net flux is a function of the predicted net flux. It also tells you the mean squared error, and it tells you the mean squared error skill score or MSE skill score. So when you plot an attributes diagram for regression, that blue shaded area is where the MSE skill score is positive as opposed to the Breyer skill score. But the Breyer score is just the MSE for classification. So they're very similar things. Second method, the spread skill plot, you can use it for classification or regression. It tells you the model error as a function of the predicted model spread. If the uncertainty is perfectly calibrated, the spread skill plot follows the one-to-one line. And then the PIT histogram, you can't use it for classification because the only possible PIT values for classification are 0 and 1, because the label can be, if the label is a yes, it's exactly 1. If the label is a no, it's exactly 0. And then all the probabilities in your predictive distribution have to range continuously from 0 to 1. So if the label is, if the true label is a no, the PIT is always 0. If the true label is a yes, the PIT is always 1. And that makes for a really boring histogram when you've only got 2 possible PIT values. You just have a spike at 0 and a spike at 1 and nothing in between. So only use the PIT histogram for regression. What it tells us is the distribution of PIT values or probability integral transform values. If the uncertainty of the model is perfectly calibrated, the distribution is uniform, so the PIT histogram is flat. And the fourth method, the discard test, also can be used for classification or regression. It tells us the model error versus the discard fraction. If the model's uncertainty is well calibrated, error always decreases as the discard fraction increases, or as you drop more high uncertainty samples out of the model evaluation. So that's that.
So I would suggest we just take a 5-minute break because we're only 5 minutes behind. So if we could all meet up again around 10:15, 10:16, that would be great.
All right, welcome back, everyone. Ima, is there anything you want to say before I start going again?
Nope.
Okay, cool. So our next section is going to be on uncertainty quantification methods. So at this point, we've spent a lot of time discussing what uncertainty is, discussing the different types of uncertainty, discussing use cases and how uncertainty estimates are useful. And we just finished talking about how to evaluate uncertainty estimates. So now we're going to talk about methods to actually get uncertainty estimates out of a machine learning model. So we chose 6 UQ or uncertainty quantification methods for this presentation. And we think that these 6 methods represent the most common or promising approaches, but this definitely isn't all of them. So we're going to start off with quantile regression. We're going to talk about using the CRPS as a loss function. We're going to talk about parametric prediction, which is, for example, predicting the mean and standard deviation of a Gaussian distribution, or predicting the scale and shape of a gamma distribution, stuff like that. We're going to talk about deep ensembles, and then time permitting Monte Carlo dropout and Bayesian neural networks. So next slide, please. Okay, so the first method I'm going to talk about, and it's called quantile regression. So this method involves directly predicting the quantiles of a probability distribution. So this means that for each data sample, instead of predicting a single number, which we usually call the mean prediction or the expected value or the max likelihood estimate, we're predicting several numbers, and those several numbers are quantile-based estimates. So in early work, as in back in the 1950s, median regression was often seen as an alternative to least squares linear regression. So least squares linear regression predicts the mean, and median regression predicts the 50th percentile instead of the mean. So for skewed distributions, often median regression was preferable to mean regression. But since this early work in the 1950s, a lot of people have used quantile regression to predict many different quantiles of the distributions. They'll predict the 5th percentile, the 25th, the 50th, the 75th, the 95th, the 99th, the 1st, et cetera, et cetera, et cetera. And I should say, I'm focusing mainly on neural nets here, as most of this presentation does, but quantile regression works for many different types of machine learning models, not just neural networks. So you can use basically anything that has a loss function. You can plop in the quantile loss function and just use it. So you can do this with a linear model, for example. So next slide, please. Okay. So like I just said, the trick to doing quantile regression is to train a model with this quantile loss function. So in this, this equation, there's 2 cases. The one case is on the top and the second case is on the bottom. So the first case is if the true value is greater than the predicted value. So y pred q is the predicted value corresponding to quantile level q, and q can be anywhere between 0 and 1. So for example, if you're predicting the 25th percentile, Q would be 0.25. So the top case in this equation is where the true value is greater than the prediction, and the bottom case is where the true value is less than the prediction. So like I just said, Q is the desired quantile level, Y true is the correct value, and Y pred Q is the estimated value at quantile level Q. So I'm not going to go over a proof to show exactly how this works. You may want to convince yourself later. I will just state without proof. Large values of Q penalize underprediction more than overprediction, which encourages the model to output a large value for Y pred Q, and then small values of Q, small quantile levels, penalize overprediction more than underprediction, so they encourage the model to output a small Y pred Q. So for smaller values of Q, you typically get smaller Y pred Q, and for larger values of Q, you get larger Y pred Q. In other words, smaller quantile levels give you smaller predictions, larger quantile levels give you larger predictions. Next slide, please. So to estimate multiple quantiles with neural nets, I think the most common approach in the literature is that people train a separate neural net for each quantile. So if they want to estimate 10 quantile levels, they're training 10 different neural nets. And because in this case, the different neural nets are trained independently, that approach doesn't prevent the problem of quantile crossing. Quantile crossing is what happens when you increase the quantile level, but then somehow your prediction decreases because models have error and they do weird things, and sometimes that happens. So an example is, let's say you're predicting rainfall and your 25th percentile prediction is 30 millimeters, but then your 75th percentile is 20 millimeters. That can totally happen if you're training a separate model for each quantile level, but obviously it's not valid. As you increase the quantile level, the value needs to always increase. So because of this problem, we've developed a novel neural net architecture that completely prevents quantile crossing. There's a bunch of tricks to this. The first trick is that you use the same neural net to predict all quantile levels at the same time. But then there's other weird stuff you have to do to enforce monotonicity. So to make sure that the predicted value always increases as you increase the quantile level. And I'm not going to go over the nuts and bolts of how we did this. There is a Jupyter notebook showing you the nuts and bolts, and there's lots of commentary inside that Jupyter notebook with equations and such, so that you can understand what the code is doing. Mainly what I want to say is that we implemented this monotonicity constraint with add layers and the ReLU activation function. And I thought it was really neat that we could enforce monotonicity as a hard constraint inside neural networks. And there's lots of other applications where you may want to enforce monotonicity. You may want a prediction that increases along some axis or decreases along some axis. And you could use a very similar approach to accomplish that inside neural networks. So just using add layers and ReLUs to create a hard constraint. Next slide, please. And I think this is the one I plan to skip. Yeah, that's a little bit advanced topics for today. So I'm going to skip this slide completely, and I'll just say that that's in the uncertainty quantification paper that we've shared the manuscript for. So I'll turn it over to Marie now.
Thanks, Ryan. So I'll talk about the next two methods. The first one that I'll talk about is using that CRPS score as a loss function. In this method, any machine learning model with a loss function, you could adapt this method to your problem. And the idea behind it is use CRPS as a loss function during training. We've got the math on the slides. I don't want to go through it in detail. You can see it in the slides or in our paper. But I think the main things to take away are, so we're using that negative orientation of CRPS. That's what the CRPS star is. And that's just because with the loss function, you want to minimize, right? So if we use the negative orientation, that means that we're going to minimize CRPS star to get our best result. And the other thing to keep in mind, again, is that if we only have one ensemble member, this orange term on the right, the spread between the ensemble members drops out if we only have one. And then this is pretty much just the mean absolute error, the absolute value of the difference between our prediction and our truth. Next slide, please. So if we implement a probabilistic formulation of the CRPS as a loss function, we can get probabilistic predictions like you see here on the left. So our work is based on a package to do this developed by Stephen Bry at the Climate Corporation. You can find links to that in the additional resources we've provided and at the bottom of the slide. So one thing that CRPS does well is that it captures different regimes. So you might have something like precipitation, where a lot of the days there is a complete non-event. And then on days where there is an event, that event may or may not follow a normal distribution. So you can see here that we've got blue. So or orange, sorry, blue is our truth, orange is our CRPS. You can see we've got orange that captures our events, and you can't see it here, but we've also got orange that captures our non-events. So we do well at capturing different regimes. We don't need to know the distribution of the data a priori, which is handy. But we need to evaluate carefully. If we just looked at the mean, for example, the heavy green line and the heavy orange line on our left-hand plot, you can see that our orange is kind of being averaged between the two regimes. So if we just looked at this plot, we might think, oh, this sucks. Why are we using this? But if we go and actually look at our CDFs and calculate that CRPS score, measuring the area of the two curves between the CRPS, we see that the difference between the green and the blue is much, much bigger than the difference between the orange and the blue. So our orange model is actually better, but it's not necessarily being captured by the mean. Next slide, please. And yeah, this is just sort of a summary, some recent work using CRPS as the loss function, including that Bry 2021 package that we used. We've got a couple of example notebooks for people to go and peruse, including one with the CRPS loss function and the other methods that we're mentioning here. And again, we've got a link to the draft version of our paper talking about all of these. Next slide, please. So our third method, parametric prediction, I'm only going to talk about this really briefly. We've listed a paper here by Barnes et al. That gives a lot of detail about how to implement this in Python. And we've also linked our own notebook showing how to code this as well. So again, please explore these resources at your leisure. To summarize, this approach involves having your model predict a probability distribution instead of a single prediction. So we would predict a mean, a variance, a skewness, and a tail weight, for example, and use those to construct a probability distribution. So this method is pretty straightforward to implement. You don't have to change your model architecture. You just change your output layer and your loss function. So that's kind of nice. And you don't have to assume anything about your data, like that it's linear, that it's normal, that it's homoscedastic, et cetera. The main downside to this approach, though, is you do have to specify a distribution beforehand, as that informs your choice of loss function. This Barnes et al. Reference covers that and provides some suggestions in that department. But yeah, again, these two resources here are really, really detailed about how to actually code this up. So we're just going to send you there if this is something you think you're interested in. Go ahead and go to the next slide, which I think is going to be Douglas talking about deep ensemble.
Thanks, Mary. Yes, thanks for introducing the probabilistic method. So here that we're going to talk about something called deep ensemble. And the basic idea of deep ensemble is to use ensemble method to quantify the uncertainty. So ensemble technique has been using very diverse ways to quantify the uncertainty based on a very diverse model trained on slightly different data or feature or initialization to estimate the predictive uncertainty. And so bootstrapping or the bagging are the most commonly used ensemble techniques. And on the right side, just cartoon showing what ensemble looks like. So you have the training sets and then you separate them. There's one way you can separate them into different data sets, or in each data set, you can select different features to train your model, and then you come up with ensemble model estimates and as well as uncertainty out of it. The next slide. And so here, probably many of you have heard about the random forest. That's the classic example of the ensemble technique that random forest is a combination of multiple decision trees trained from the data. And so decision tree is basically just one tree-based model trying to either do a classification or regression. And then people start to using the ensemble method, trying to generate a random forest and an ensemble of diverse tree models to combine outputs, generate the ensemble to come up with a predictive model and for the prediction. And that from the philosophy is that from a single learner or single model to ensemble of multiple diverse learners models that can generate better predictive results of it. Next slide, please. And the ensemble for the uncertainties it's not anything new. So in both weather and climate community, that we have been always using ensemble to quantify and communicate the uncertainty of a predictive system or predictive model. For example, in climate, you always have the ensemble models, and then use the ensemble model to really capturing the variability of the uncertainty that may come out for the climate projections. Next slide, please. And now let's talk about deep ensemble. So deep ensemble is using the similar idea that we have we have one input data sets, and you can use one random generation initialization to start to generate a neural network model, which generates the distribution or the parameters, including both mean, standard deviation, for example, in this case. And then you can repeat this process to multiple random initializations. If you go to next slide, please. That you can generate multiple neural network models using different random initializations. You're still using the same data set, but just using a slightly different random initialization in here. And so you can create multiple different probabilistic predictions for different models. If you go to next slide. And then you can combine those the model output from multiple neural network models and tend to generate a distribution of the final outputs. And that, if you assume it's a uniformly weighted mixture, you can basically just doing an average of the prediction from each individual random neural network models. And this is a paper outlined by in this reference. Down below, you can find more details about how the deep ensemble has been implemented. And because, like Mary mentioned, that you don't really need to do a lot of tweaking about traditional neural network models. So it has been really popular, and to do the uncertainty quantification as well. Next. So again, going back to the reference paper, that the red dots are the true observations, and then blue line are the truths that we want to generate based on the neural network models. And the shaded area are using five ensemble members in the deep ensemble to generate uncertainty from this for this toy data set in this case. If you go to next slide. They also trying to demonstrate why the quality of deep ensembles of the uncertainty measurements, uncertainty quantification. So it shifted the original data. So this is a classic computer vision task of using the image nets. And then the original data, if you apply the models, that you can get really high quality and of the accuracy and also the uncertainty estimation. But then if you shift the data with adding noises and other ways to modify the data, that it generates the deep ensemble still can capture the uncertainty even under those data shifts. If you look at the green bars there, the deep ensemble consistently outperforms a lot of other methods when quantifying the uncertainty. There's a recent paper in 2019 about how to if you can trust your model uncertainty there. Next slide, please. And here just an example that we use in our satellite product retrieval, so that we are trying to use a long-term satellite data records, high-resolution infrared radiative sounding instruments to estimate temperature and humidity at different pressure levels. We're doing it at 10 different levels. And it's basically a 3-layer neural network model. And that we have in the earlier version, we do not have uncertainty quantification. We just have a estimation of the temperature and humidity there. And now we're trying to add in uncertainty quantification for it, because the climate monitoring often requires the quality or uncertainty of those measurements. And so we use a simulation data trying to test if this deep ensemble model can generate a realistic uncertainty measures. So when we use in this simulation measure, and we have known the 95% quantile, the confidence intervals, and then use a deep ensemble, which generates uncertainty estimation at closely to the 95% confidence in the confidence interval estimation. So this is something we find is really promising, and we're currently working on a paper to describe how we use deep ensemble to quantify the uncertainty in this temperature profile retrievals. Next slide. And just really quick comments about deep ensemble. So I really like this cartoon from Blodgett from Google Brain that is demonstrating how some different methods to use for like uncertainty quantification. For the very single neural network based way to do the uncertainty quantification, the quality can be low, but the time and memory required for the computation is really also low as well. But then when we move on to those ensemble methods or Bayesian-based methods, that it really can get a high quality uncertainty quantification, but oftentimes requires much higher demand on computing time and also computing memory. So there's always a trade-off between the computational cost and the quality of the uncertainty estimation. And so it's really hard to generalize for different use cases. So, but there are a lot of ongoing efforts trying to make those ensemble or Bayesian-based methods more practical and easy to use and efficient. And I believe that I will turn it to Aiml.
Thank you. Yes, and so just to get us back on time without rushing, I will go through the remaining two methods just very briefly without a lot of details. So don't worry, and let's first take a 10-second break because I think we've been going pretty fast. So just a 10, 15-second awkward silence. All right, I hope you got a few deep breaths over here. So our method number 5 is Monte Carlo dropout. And that one is very popular because it's very easy to implement. So the idea, you may have used dropout already to come up with a network that doesn't overfit. So the key idea is a regular neural network is just shown schematically here on the left. But the same network with 2 neurons dropped out is shown on the right. So the whole idea of dropout layers, that's the standard function in PyTorch and TensorFlow, is that you can include a dropout layer, and what it will do is that it will randomly drop different neurons during the training. And the whole idea of that is that your neural network learns to not just rely on a single neuron. It will kind of distribute the task more between different neurons, because at each training step, the neuron that it was relying on might get dropped out. So it kind of distributes things moreover. Okay. So that was the basic idea, and I won't go into detail in this slide, but just keep in mind, so you can choose a dropout rate. If you choose a dropout rate of 0, neurons are never dropped. If you choose a dropout rate of 0.5, you drop about 50% on that layer, and the dropout rate becomes an additional hyperparameter. And again, we may do that during training to not overfit our models. But I will just skip to right here. What you can do is you can also turn on the dropout layer during operation, so during testing or operation. So the whole idea is then you have a sample coming into your neural network, and your neural network now has been trained so that it will work moderately well when you drop some of the neurons. So you now just go ahead and randomly drop some of those neurons, and each combination of dropping a sample of neurons will give you one neural network. So you sample it kind of once, gives you one neural network. You sample it again, you get another neural network, you drop another set of neurons, it gives you another one. So you get instantly, for each sample, you just do that anew. So you get instantly this k different neural networks, and each one is going to give you an answer. And that gives you an ensemble of predictions. And the pros of this approach is that it's extremely easy to implement because you already have dropout layers in the neural network software anyway. The only thing you have to do is in TensorFlow, for example, you just have to set that the dropout layers stay during training, stay on equals true, done. The problem is that it's slow in fairness time because every time this X comes in, every time you have a new sample, you have to sample which neurons you drop and then come up with the different predictions. So that takes more time. And just by itself, by just throwing in the dropout layers, we have not found it to give great results. So you may want to combine it with TAI4ES and a bunch of other things, but now you have the basic idea of what Monte Carlo dropout does. Okay. All right. Very quickly, basic idea, moving on to Bayesian neural networks. And again, I apologize that we go slow, really pretty fast. You can read the paper, and also Monte Carlo dropout and Bayesian neural network are probably the most well-documented ones. So it's easy to learn those on your own. We're just trying to give you the basic concepts here. Very, very basic idea of Bayesian neural networks. You can look at them as a generalization of Monte Carlo dropout, but the key idea is if you have a standard neural network, your weights and biases are to be learned, but they're just single numbers to be learned. And the activation function is fixed. It's pre-selected, right? If you train a Bayesian neural network, either the weights and biases or the activation functions in the layers are probabilistic. So we will only focus on the simpler type where the activation functions are actually fixed, but the weights and biases are modeled as probabilistic. So rather than trying to learn a single number for each weight and each bias, you're trying to learn a probability distribution for each weight and bias. So that sounds mega complicated. So people have done a lot of simplifications. So again, you see here a standard neural network, which has just a single number, maybe learned 0.9 for this one, minus 0.2 for this one. If you move on to Bayesian neural network, instead of having a single number for a weight, you may say, oh, I'm assuming it's normal distributed. So instead of learning a single weight, you learn two different numbers. You learn mu, the mean, and sigma, the standard deviation. So again, that's a very common simplification. Just assume that each weight and each bias is normal distributed. So instead of having one value to estimate, you have to learn two values. And then once you do that, you can basically, and I should say TensorFlow's probability library provides probabilistic layers for you to do this. So in theory, we can just replace deterministic layers by probabilistic layers using TensorFlow probability or equivalent things in PyTorch. But in practice, it's not quite that easy because they're pretty large memory requirements, and there are also large computational requirements for training the neural network. Because this now has twice as many parameters, and the whole thing is a little bit more complicated. So based on experience by other groups working in environmental science, most research groups that I know who have played with this, we haven't ourselves played much with Bayesian neural networks, but most research groups run into problems as soon as they have more than 2 or 3 probabilistic layers. So most research groups just, even on big computers, they run out of memory. There is, however, a success story. One group successfully converted all the layers of a deep, complex neural network, in fact, a ResNet, into probabilistic layers, and they used their own implementation. Which group and application could this be? Well, you've already seen it mentioned in the presentation. It's the Orris-Gannon paper. And I won't go into details here, but I will just say they've taken it, it's deterministic ResNet, so that's a very deep, large neural network with lots of parameters already. And they replaced all of the layers, the deterministic ones, with probabilistic ones. Everything is a Gaussian distribution, and it seems to work for them. So look at that paper if you're interested. Again, impressive implementation. I'm very impressed by their work that they could make it work. So it seems to be possible, but it's not as trivial. So that's kind of my key takeaway. With that, I'm just showing you the results again, without going into much more detail. And with that, I think we just wanted to share some other resources here, a bunch of other papers if you want to do more reading. of how different types of uncertainty quantification methods have been already used in the environmental sciences. Here are a bunch of interesting papers. Somebody asked how you can separate into aleatoric and epistemic uncertainty. I will just point to this paper, but all of these are really good papers if you want to read more on your own. Here are resources, and you all have access to the slides, so you should have the links. And I also posted the links for this one, and this one are in the Slack channel, in Slido, and these two are actually part of this one. So you have all of those resources, and big thanks again to Ryan and Kathy for actually for putting together those notebooks for you. And with that, we just have another few accessible papers, because I will tell you, all this uncertainty quantification, a lot of those methods are really hard to read at first. And so these are some of the papers that we found easier to read. So you may want to start with those, but of course, up to you. With that, we have time for breaks and questions. Are there any questions in Slido that we should answer?
We've got a question about extreme events and a question from Philippe about estimating model uncertainty of a calibrated machine learning using either repeated calibrations versus using multiple dropout versions of the model.
All right, why don't we start with the extreme events? That's actually a tricky one. If you use a Bayesian neural network, you cannot assume automatically that it will get all the tail really well. That is one of those things where I think we still have to wrap our brain around how to best do this. It is a very important question. I don't know whether anybody else wants to jump in and say something about that, or anybody in the audience who's actually played with that. DJ, do you want to say something?
Yeah, on the question about, I guess it's on the long tail distribution question. Emma, sorry, I was answering questions and got.
Okay.
But which one did you want me to add more to?
Yeah, the long tail. I think that's an important one.
Yeah, I think one of the big challenges, especially with Bayesian neural networks, is that there isn't really a clear theoretical distribution that neural network weights should have. People assume Gaussian because the Gaussian only has 2 parameters and it's easy to calculate and covers a wide range of values. But there's no reason it should be Gaussian. So theoretically, you could try using a Weibull or Pareto. Although the issues with some of those would be you couldn't have negative weights in those cases, which neural networks generally have. You assume that they could have any kind of weight, but I think there are long tail distributions that can be both either positive or negative, or I'm sure you could finagle it if you really wanted to. And there's also I think there are versions of the Gaussian. I think in Libby Barnes's paper, she has a distribution that does have a tail control built into it. So there would be some other distributions that I think are somewhat tractable, and you can estimate the parameters and get something. The tractability is also an issue if it's a distribution that has various mathematically complex terms that are computationally intensive to calculate, then that can also slow down your training. And as shown in that one diagram, yeah, a lot of these methods you'll get you a better uncertainty estimate, but the computational complexity can go up quite fast if you're not careful.
All right, I think with that we should take a well-deserved break. Let's do a 9 to 10 minute break. Or okay, let's come back at the full hour. So 11 a.m. Mountain Time. I will see you all back in 10 minutes.
All right, so we're back on the hour. So as people trickle back from the break, we're going to kick off with the risk communicating uncertainty section. And so with that, there's also a note we're going to make now, and I'll throw this in Slido later, is we do have a risk communication for different, or actually, I think it's up to a couple of sections, RiskCom tutorial. So if you're interested in some more of these ideas on the risk communication side, Ann Bostrom led a really great session along with other members, Julie Demuth, Mariana Keynes, and Andrea Schumacher on these topics. And we'll throw that link that you can get to on the AI2 website, AI2ES website there. So if you get more of these things, there are more resources available. But on that note, getting things started with the communication side, I'm going to revisit this image that we showed at the beginning of this series. And so if you'll notice, we have kind of that question that was there before, how can we best visualize or quantify, visualize, and communicate uncertainty around this cold stemming model? And so with that, we're going to actually throw this back to you because you've been thinking a lot about uncertainty from a lot of different levels, but we want to put you back in this end user space and thinking about how we would start to characterize this for an end user. So if we can pop that Slido poll live, you'll have the question kind of open and we'll see how can we best quantify, visualize, communicate uncertainty about a model like this example here. So I'll stop sharing and let the results come in. Okay, so show confidence intervals in addition to mean prediction. All right, great. So showing kind of some range around uncertainty. It's a good way. How else can we communicate, quantify, and visualize certainty? Showing error bars. Yep, so related to confidence intervals. Make lots of sense, technical audiences, but depends on the user. Yep, so there's different levels of knowledge that you need to have for that, or kind of different literacy or numeracy. Depends on the problem and context. Ooh, good, someone's listening. And the user, yeah, for sure. Confidence intervals, bands, various levels. Confidence sense, visuals are key. Okay, great. Forecasters often want to know the possible worst case scenario too. So okay, having kind of different types of uncertainty. So maybe like the onset of an event, or when like the earliest it could happen, or the latest something could happen. Great. So it depends on who you're talking to. Again, awesome to see that. Absolutely do not show a graph of uncertainty to an unspecialized end user. Okay, so thinking about some of these pros and cons to different points. We talk about the tendency of a model to over or underestimate. Okay, so kind of showing the relationship with a particular model. And that comes into how we picked case studies and what we wanted to communicate with those. Do we show the best hits, worst misses, both? Communicate failure modes using case studies. Yeah, so connecting to yesterday's materials for sure. That's awesome. We still got 5 people who'll let you get back into this here. Yeah, it needs to be as simple as possible for users. Allergic to unnecessary complexity in the middle of an extreme event. 100%, because like Andrea talked about in day one, some of those contexts of people making decisions that are really fast and really short. In terms of distributions and uncertainties at various phases of an event, face-to-face communication. Yep, so you can use a lot of different types of ways to do this. Okay, that's great. Awesome, very, very good. This will be a good setup for where we're going next. And so we can actually flip back to our screen here, and I'm going to share some slides. And so with that, I'm going to bring you back to day one. You're kind of pulling some threads together here. And we want to make sure you're thinking about why are we asking about risk, right? Because trust is what we've most been focusing on. But if you remember in our definition of trust here, so trust is the willingness to assume risk, right? So this is an integral part of how we're thinking about trust, is this risk communication part. And a big part of risk is uncertainty, and how we communicate that is also really key. So I'm going to pull in the wonderful Ann Bostrom, an expert and pillar in the field of risk analysis and risk communication, to help talk us through a little bit of these points here on how we characterize and communicate this uncertainty.
Thank you, Chris. And so you all know we have deemed Chris the king of Slido. So thank you very much for setting that up. So risk is generally defined as a probability times a magnitude. In other words, it's a function of how uncertain and how big the harm is, as cited by Avon and Wren in their 2009 article where they discuss risk and what it means. So that uncertainty is a really key point here. We can think about the understanding the magnitude of the consequence or harm depending on both the relative size and the absolute size of that harm. So for example, hail, is it going to damage your roof a lot or a little? And understanding that absolute size requires understanding the metric that's being used. I've heard you asking a lot of questions about metrics here, so you can understand that metrics can be very technical and sometimes they're hard to understand. So consider the hail sizes mapping when you think about those metrics, sometimes people think about golf balls rather than centimeters or inches. Mapping is easier than metrics. So we know from a lot of research that people are really good at getting the relative or rank orders of sizes. So relative sizes, like that golf balls are smaller than baseballs, then at estimating the exact metric, as Amy showed in her slide, where we saw those really lumpy estimates of hail size. However, some people maybe care less about the size of the hail than they do about the size of the bill they're going to get for repairing their roof from the hail damage. So even relative perceptions of the magnitude of the risk can differ by users if they're based on different metrics. And metrics in environmental science in particular can be really challenging and unfamiliar to people. It can be hard for people to make sense of them. So communicating the uncertainty is even more challenging. For example, communicating probability so they're meaningful is challenging, in part because of the challenges of understanding both the mapping and the metrics, especially for very low or small probability risks, which can be important if they have really big consequences. So in other words, if they have a catastrophic potential, they can be harder to understand, and that's a dangerous, usually high pressure decision context. So I'll dive into some details on communicating uncertainty in a minute. But before I do, it's important to realize that when you're communicating about risk and uncertainty, that people care about more, they care more about magnitude than they do about probability. And they may even want to expect to hear about other factors that they care even more about than either of those. So next slide, please. So what we can see here is something that's called the risk factor space. It was developed by Paul Slovic quite a long time ago. You can see this is a 1987 science piece that's quite famous, and it has two dimensions. The first dimension is the dread risk dimension, which is on the horizontal, and the second is the familiarity dimension, which is on the vertical. And we can see here that these they've sorted here a bunch of technological risks. So notice in particular in the right-hand upper quadrant, the DNA technology. You might think about AI as being a relatively new and unknown technology, for example, like DNA technology in the late 1970s. And over the last several decades, Paul Slovic and his colleagues, Brooke Fischoff, Sarah Lichtenstein, and others have found the judgments of risk acceptability vary on these two dimensions, how dread a risk is and how familiar it is. And the most dreaded and the most unfamiliar in that time was for DNA technology up there in the far upper right-hand corner. Is AI up there? Well, we don't really know. But that is a function of whether the people judge the exposure to the risk as voluntary or involuntary, if the risk can be managed or reduced, is it controllable, and does it harm a lot of people all at once or have a catastrophic potential? So this factor space was derived from doing a factor analysis, which is like a principal component analysis on all of these different questions here. And this is kind of small, but they are these questions about whether something is controllable, whether it has a catastrophic potential, for example, and whether scientists understand it or other people understand it and whether you can see it. So really important to think about when people are making decisions about whether they're going to do something in a risk situation, because if they don't find the risk unacceptable, they're likely to do something. Next slide, please.
Do you want to look at the poll results? We have them coming in too.
Oh, okay.
So we have on our,
let's do it.
Think about risk and benefits around AI. We'll see how people compare on these metrics. So I'll stop sharing.
Yeah.
You can see some of those results. So it looks like we have a lot of people engaging in those. So we should have some interesting stuff, thinking about people's own risk perceptions. Yeah. So is AI risky for society? Looks like most people are, about half people exactly are saying yes.
I wouldn't have expected that, actually. I would have thought that this crowd would have said, wow, not so risky, really important.
We got some indifference in there a little bit in the middle, not agreeing or disagreeing. Yeah. But then we look at benefits and then we see, there we go, that's kind of what you'd expect to see for sure.
Exactly, even stronger agreement, but still some hesitation.
Yeah. And then we put into a specific context, how does this change? So you're concerned about damaging the environment from the AI and ML here. So a little bit more than when we said it very generally, which is interesting. So we put a more specific point on there, slight increase over the side.
Yeah, that's an interesting question too, because we can think about how people understood it. How likely is it that it will damage the environment? We still a large plurality saying likely.
Yeah,
possibly because of the ethical issues around carbon footprints of AI and the carbon footprint of AI. Those heavy duty probabilistic models that Emma was talking about.
For sure. And it relates to when we talked about those FAIR principles on day one. People really seem to grab onto the ecological aspect of it as well. So that's awesome.
Yes, excellent.
All right, thank you. We can share back to our other screen here.
Great. Okay, so moving from the risk factor space back into the risk communication space. Oh, oops. Yeah. So we could take your answers to those questions and put AI in that risk factor space if we'd asked all of those 18 questions that they had there. I think it's something like that. It's a large number of questions, which we figured we didn't have time for. But given how beneficial that you thought risk AI is, that it probably wouldn't have rated up there where DNA technology is right now. So next, yeah. So Vanderblis and colleagues in 2019 deconstructed the communication of epistemic uncertainty based on what's called the Laswell model of communication. And they do that in this figure here. The figure summarizes in a very succinct way what we know from research on communicating risk and uncertainty about what matters for trust and decision-making. So we're going to use this to just deconstruct a graphic of the type that was used earlier and that Chris showed you. And so just to summarize briefly, we know that it matters who is communicating, what they're communicating, in what form they're communicating it, to whom they are communicating it, and to what effect. In other words, what are those people they're communicating it to going to do? Next, please. So we'll start with who communicates. How does that matter? Next. So we know from research that trust is relational, and that it matters whether the people who are communicating have good intentions, and if you think that those intentions are aligned with your best interests. So the value similarity between the communicator and the end user is really important. Do they have the right expertise? Are they competent? So those are two aspects that we think about in terms of the people who are assessing the risk and the people who are doing the communication. And so in this graphic that Chris showed earlier, we can see that it states that IBM and TAI4ES are providing the Ensemble air temperature predictions that we're seeing here. So people will be judging in part whether they trust this information based on who communicates that, who has produced the risk and assess the uncertainty, and who has assessed the uncertainty, not produced the risk, and the people who are doing the communication. In this case, they're both. Next, please. So I show here on the right a picture of Marshall Shepard and another picture of Jeff Masters from Underground. Tried to pick people who would be familiar potentially to this audience. There has been research showing that among the many popular public figures who are in our everyday news feeds, for example, around the world, local weathercasters tend to be trusted for information about weather and climate. Others, like politicians with unaligned interests, may in fact communicate uncertainty strategically. And there's been work by Naomi Oreskes and others showing that, in fact, the use of strategic certainty argumentations, what Bill Freudenberg calls scams, can cause people to doubt whether or not they should do anything. So it can cause them to delay their decision making and hesitate. And so people tend not to trust them as much. Next, please. So what are we trying to communicate matters as well. The object, the source, the level, and the magnitude of what we're trying to communicate. Next, please. Vanderblis and colleagues focus on facts, numbers, scientific models, and hypotheses, exactly the kinds of things that we've been talking about in this summer school. And we can see here highlighted under research that here the communication is about ensemble air temperature predictions, and they are neural networks. So next, please. Also, Douglas and others have highlighted this entire production line, and that uncertainties can creep into every step of the way. So that means data and model variability, biases, or other shortcomings are also important in terms of what we're communicating. And these are all considered direct uncertainties in the Vanderblis piece, which summarizes what we know. Next, please. Very importantly, the indirect uncertainties matter as well, or the quality of evidence, and how big the uncertainties matter in decision making a lot. An example of indirect uncertainties is shown here on the right. This was discussed by Andrea yesterday in the context of these model cards. Those are like the quality of evidence and what we know. Oh, next, yeah, that was good, Chris. So in what form are the uncertainties expressed? Next, please. So we know that quite a few things about communicating numerical risks, though there's also insufficient testing of this in context, so there's a lot more to learn. David Spiegelhalter summarized in an annual review piece in 2017 quite a few of the takeaways that we have from the research that's been done so far. It's important in contexts where you're communicating risk to use absolute risks, but also to provide the relative risks when you're dealing with potential catastrophic events. So how likely is it to harm a number of turtles, and how likely is it as a certain event compared to some other event, and for example, to harm a certain number of turtles. For single unique events, you can use the percent chance as, if possible, or if necessary, 1 in X. 1 in X is not quite as accessible a format, but it does tend to increase people's concern or attention to something. When appropriate, it's important to express the chance as a proportion, a frequency, or a percentage, and it's crucial to be clear about what the reference class is. Next. Here's a quote emphasizing the importance of that clarity. And this is really important in the weather and climate context. More important than the choice of format is being absolutely clear as to what the probability actually means, which requires really careful specification of the reference class. An average over what time, over what space. Next. Spiegelhalter offers a number of other specific pieces of guidance here. It's important to provide percentages or frequencies both with and without the outcome that you care about to avoid framing biases. You want to keep the denominator fixed when you're making comparisons with frequencies, and you want to use an incremental risk format. So how much bigger is the risk? Be explicit about time intervals, and this crowd probably doesn't need to be reminded of that. It's very important in environmental and weather context. Be aware that comparatives can create an emotional response. People can be quite upset about something where they feel that the comparison is inappropriate, for example. And it's also for more knowledgeable audiences, you can consider providing quantitative epistemic uncertainties about the numbers and qualitative assessments of confidence in the analysis. And we've had quite a bit of discussion here about that, those quantitative epistemic uncertainties, not as much about the qualitative assessment of confidence in the analysis, but that's something that's been commonly used recently by the IPCC, the International Panel on Climate Change, for example. More sophisticated metrics can be used for technical audiences, but this only serves to exclude the others and other people who don't have that technical expertise. And I think one of you emphasized in Slido in that question that Chris started with, that complexity can exclude lots of people, so you might want to avoid it, especially in high pressure situations where people don't have the technical competence to understand it. Next, please. Vanderblas and colleagues also provide a very clear listing here of the decreasing precision of ways in which you can communicate uncertainty. So a full probability distribution is going to be the most explicit way of communicating epistemic uncertainties quantitatively. You might have a summary of a distribution like the mean and the standard deviation, which will have less precision in terms of communicative precision. You might use a rounded number, a predefined categorization of uncertainty, or a qualifying verbal statement, a list of possible scenarios. And we heard all of these as possibilities for how you might communicate risk and uncertainty in the Slido question that we started with. So you're certainly all aware of these. Worst and least precise is no mention of uncertainty, and worst is explicit denial that uncertainty exists. Next, please. So it also matters what the characteristics of the audience are, their relationship to what you're talking about, and the relationship to who is speaking about those uncertainties. So to whom is a really important factor. Next. I'm just going to highlight 3 of the many things that we know about characteristics of to whom, the audience or the end user, that matter. One is numeracy. So about 1/4 of the US public, for example, is enumerate. And I don't know the statistics for other countries, but I suspect they may be slightly smaller. Ellen Peters and colleagues found that when you ask people which is larger, 1 in 100,000 or 1 in 10,000, about 10% of respondents had trouble with even this kind of comparison. And numeracy increases people's use of heuristics, so their use of rules of thumb or mental shortcuts to try to solve a problem instead of doing the actual calculations. So when people are enumerate, or if they're under stress also, they're likely to do what we call fast thinking and use an impression rather than a calculation to discover what's happening. Next. Graphicacy also matters. And graphicacy is discussed by Lace Padilla and her colleagues in several different papers, which many of you might find interesting to look at, where they actually do tests of what happens when you show people different kinds of visuals or statistical graphical representations of uncertainty. And what they're showing here in this diagram that's probably too small for you to see is what they think happens in the cognitive process when people try to understand a graph. And they're showing a bar chart here. And the big important difference here is that when you look at the bottom, you have slow thinking. People are actually doing the calculations to figure out how large something is, what the magnitude is. It's 2.2. Whereas in the top, they're doing fast thinking, and they're just going to make a guesstimate. And what they're trying to do is pattern match. They've seen a bar chart before. They're interpreting the bar chart based on their understanding or familiarity with what a bar chart represents. And then they're doing a quick pattern match to guess what's happening, basically. So it really matters the extent to which people are familiar with the type of graph that you're showing, and also their ability to take the time to and have the capacity to do those calculations and deliberations that give them a more accurate understanding of what the uncertainty is that you're representing. Next, please. Also, mental models matter. So what people think is going on, what their understanding of the causal processes are that are behind what you're showing can mess up whether they're paying attention at all to the communication that you're giving them about the uncertainties. This specific quote shows that when you ask, when a hurricane is coming, when somebody wants to know how strong it is, and a weather forecaster tells them it's going to produce 15 to 20 inches of rain, because they know that storm surge is one of the most dangerous aspects of a hurricane, the person asking is going to feel like their question isn't answered. They want to know how strong it is based on the wind, because their mental model is that a hurricane is about strong winds, and that's the important risk. And they will often typically use a hurricane that they've experienced as a reference point or benchmark. So in this case, this was in Florida. This is an interview that was done in about 2014, I think it was. Actually, it was a little bit earlier, and they were using Hurricane Andrew as a benchmark at that point, which was a Category 5 hurricane. So they were doing a comparative interpretation of information about risk and uncertainty based on their actual experience, and it was recent experiences in that case. So the benchmark has probably changed now. Next, please. Communicating, then the last part here is to what effect. So what is going to happen when you communicate these uncertainties? Is that going to change people's decision making or not? Is it going to change what they're thinking, their cognition, what they're feeling, their emotion, their trust in the information, and then how they behave and decide? Communicating uncertainty can increase trust in the information, affect attitudes toward the messenger, and may sometimes even delay decision-making, according to Spiegelhalter's summary of the research. And many of you have probably experienced this yourselves, or experienced this when you communicate the uncertainty to somebody about an environmental prediction. But there's a lot more research that's needed about the specifics on this. The little balance here is indicating that in addition to all the cognitive factors that we've been talking about so far in the presentation, and also that have been discussed throughout the summer school, emotion really plays a big role. And especially when people are using fast thinking, emotion is often substituted for cognition. People will use their immediate reaction. Do I like this information or not? Does this feel good to me? As a substitute for actually doing the calculations to see if it makes a difference in the technical aspects of the decision making. And that's called the affect heuristic. And that can be fast thinking that takes place either when they're under stress or when they don't have the capacity or technical understanding to understand the uncertainty more specifically. So it's really important when you're communicating to think about that people's response to the information is going to matter. Their emotional and affective response, whether they like the presentation even, is going to matter and may actually determine their decisions as much as what the actual content is of the information. It's also important, as Chris has highlighted so many times, to think about the decision context and the user's position. What decision are they trying to make? What problem are they trying to solve? And you need to align the format with the decision. So for example, if you're communicating the 5% and 95% range, as is shown in this graphic here, 95th percentile and 95th percentile, it's important to think about presenting that in a way that aligns with the decision that they're making. In this case, they're trying to protect turtles. So they're really interested in whether you're going to go below that threshold, that temperature threshold. So you might want to say something like 5% of the models predict a temperature below the sea turtle temperature threshold. But to know how this is actually going to impact people, you'll have to test your communication, because all of these factors that we've just gone over interact. Next, please. So in this graphic, we've tried to analyze that little graph to see what these different factors are. So we'll start here on the left with who is communicating. Well, as we mentioned, it's IBM and AI4ES, and those are mentioned in a couple of places. So people do look at the logo of the logos and the source to see where things are coming for, and that's going to affect their trust, their decision making, and their responses, as well as their affective response. If we look at the red square here, it's what are they communicating? And as we highlighted before, it's ensemble air temperature predictions. That's going to matter. They may care that it's an AI prediction rather than some other kind of a set of predictions, and that is communicated in a couple of different places here as well on the graphics that maybe split their attention. In the green box, we can see there's a question about in what format, and we've got and what the content is. They've got a specific ribbon chart. If people aren't familiar with these ribbon charts, they may actually just think they may not know what the confidence band means here. The 95th to 5th, I guess it's not really a confidence band. It's a percentiles of predictions. They're gonna make up an interpretation based on their understanding. And we know that lines like this tend to be assumed to be trends, which it is in this case, and they may be extrapolating subjectively to think what they think should be going on based on their underlying mental model, for example. So it's a ribbon chart, and it's percentiles from 5 to 95, and they're going to try to make sense of that based on their prior experience and understanding. And to whom? So one of the really important decision-making or end users, people or end users here are Texas Parks and Wildlife, and they're going to care about what they can do with that information. Do they have, what kind of technical expertise do they have? Are they familiar with these graphics? Do they know the people who produced this information and the source of that information? And we know from interacting with Philippe Tissot and colleagues that in fact they have an excellent relationship and they interact with their users quite a bit. So it's a really good starting place to come from in this graphic. And then finally, to what effect? Here we're going to ultimately, the hope is that they will make good use of this information to protect turtles, but there may be other things they will do as well with this in terms of changing their understanding of what's going on at various times of the year that might be risky for turtles. Next, please. Okay, now I'm going to shift gears from our deconstruction there of epistemic uncertainty communication to talk about a couple of different specific aspects of that uncertainty communication. So one is that in most communications, people use not only graphics or visuals, but also some kinds of words. And it's important to understand that verbal phrases are vague, and in the sense that the same term, a chance or not or certain, or even terms like likely, can be used to characterize a whole range of numerical probabilities. This has been analyzed extensively with the IPCC use of verbal probabilities. We find that people often have really quite differing interpretations of what a specific verbal probability phrase means. So if we look to the right here in this table that shows a taxonomy of risk concepts by Brian Sigmund Fisher from 2013, we can see, for example, in the top row is the word possibility. That might be interpreted cognitively as something that might happen or might not happen. It might be it's clearly distinguishable from something that will or will not happen. And the level of precision is quite minimal, as we saw from the list of precision of ways of expressing uncertainty by level of precision from the Vanderbilt paper. And the valuability of this is very high because people feel like they can understand the term like possibility, and it's very commonly used. To the right of that, we see an illustrative just statement. It could happen to me, might be how people would interpret what was going on there and what they would think about it. And the emotional interpretation of that might be that they were at risk, and so they'd have negative feelings about that. And you can see several different examples here of different kinds of verbal phrases that could be used. Next, please. The semantic and the pragmatic, in other words, use implications of these expressions include that people might be using hedges, maybe, they're going to interpret an outcome valence, whether it's positive or negative. So it could be risk or hope, for example, and the directionality will matter, whether there's something they think something is going to happen or not happen in terms of the target event, like going below that temperature threshold. Next, please. So thinking about this more generally, the other issue here with communicating about uncertainty is we talked about those direct and indirect uncertainties. We've been talking about these terms like virtually certain, which are verbal terms of the sort that were shown in the previous slide. And here are the ranges that the IPCC attached those. David Badescu and colleagues found that when people actually tried to attach their own subjective estimates to them, they did not, they tended to compress their subjective estimates. So the high terms here were interpreted as actually having lower probabilities, and the low terms were interpreted as having higher probabilities. There are also those indirect uncertainties that we talked about. We mentioned that you could use the model cards to express those indirect uncertainties. Confidence is another way of thinking about indirect uncertainties, and the IPCC does this in this kind of a context where they have these different terms: high agreement with limited evidence. They try to look at the extent to which the experts that were consulted for the report agreed, and the amount of evidence that existed to support that level of agreement. So that's another example of an expression of indirect uncertainties. Next, please. Okay, Chris, I think we're together again.
All right, yeah. So all that great information about communicating uncertainty, we're going to put you back with the same example, but we're kind of turning up the heat a little bit, where we have a different plot, but we're going to ask you essentially do a little bit of role playing with this next Slido prompt. So you have this plot, and imagine that it is Saturday, February the 12th. So you can see it's right about where those, like the black dots stop in the middle here. And you're looking at this model output, and you're seeing here's where the predictions are. Imagine the blue line is what's being predicted. And the Port Authority, so someone who does not have a lot of familiarity with AI or meteorology or any of those types of backgrounds, is asking you, will the temperature go below our sea turtle water temperature threshold, which is that top red dotted line? You can see, right there on where it's almost going to hit that line, but not quite. Maybe it hits it, maybe it crosses it. We can't quite totally tell from this output. And they're interested in looking at it for the next day or two. So you're looking from about Sunday, the February the 13th through to Monday, the 14th. So we go to Slido. How would you communicate your certainty and your confidence with this question, to your user, which is the Port Authority? Will it go below? You're answering that question. They want to know, is it going to go below this line? How do you communicate your certainty and your confidence in your answer based on all of the things we've just learned? Give you some time to look that one through.
We can see this is not a gut check, is it? It's a difficult question.
Yeah, people are writing. We're going. I don't think we'll see the answer. You
Yeah.
can't quite see the answer, though. I think it's a trick. So if there's a multimedia team could show us if things are coming in, that'd be helpful.
Oh, that'd be great.
Okay, so I can see them on my side, but it's 50-50 odds that it will drop below the threshold. No, unless we have a 3 sigma event. Interesting. Maybe, but we are unsure, and it won't last long. Okay, we're still have some people writing through that. So you can see a lot of spread. Hard to answer. Also, good point. Yes, it is tricky, but these are the types of situations we're going to have to answer them in. There's a 50% chance that the temperature goes below the threshold. There's a good chance that it can go below. With roughly 50% chance the temperature will go below the sea turtle water temp threshold. No, it's not going to. But we have no predictions that are even close to being low enough. Let's see. There's a chance it'll drop below. It may go below with 40% chance somewhere between the next week and the coming one. I will say that the temperature will not go below with a fair confidence. Okay, all right. Good spread of answers here.
Okay.
Looking within the confidence interval, it's not likely to go below, but it could happen.
Excellent. So we hear, yeah, so we hear in those responses uses of the specific numbers for probability. So, and and things like good chance, which are also those verbal probability statements that we talked about a second ago, and also the directionality, showing that people are considering whether the decision that the end user is facing and how difficult it is for them to make their decision, what kind of information they're looking for to try to inform what they're doing. So now that you've thought about that a bit, let's dive into an example, a little bit more information about how to use these kinds of information in an example. So often in these kinds of a context, and not in the specific temperature context here, but often in environmental communication, we do uncertainty communication on maps. And there's been quite a bit of specific research on how people communicate in uncertainty using maps. This here is an example of the earthquake hazard mapping that's done by the USGS. And you can see here that the highest hazard is labeled in red, lower hazards are labeled in green and blue. And this is actually kind of a natural or intuitive color scheme. Red tends to be interpreted as more risky. And you can see that all along the West Coast, so I'm in Washington and Seattle, and you can see that there's a red area there having to do with the Cascadia subduction zone. And there was a very popular newspaper, a news article in the New Yorker several years ago called The Really Big One, where there were quotes from people saying things like, our operating assumption is that everything west of I-5, Interstate 5 that goes straight through Seattle will be toast. So people have a tendency to bin things. And you can see that even this uncertainty quantification does that. That may or may not be appropriate. In fact, Sievertson in her paper said an unfocused, unclassed map is a more accurate representation of the risk data than a focused classed map, because of course there's no sharp delineation between when something is going to happen and when it's not in the environmental context that we're in usually. Next, please. Here also is a quote from a scientist from work on by Thompson on volcanic hazard communication, except when you put a boundary on it, then people probably think if they're on one side of the boundary or the other, there's a huge difference, when in probability there isn't. And below this is some work by Julie DeMuth, our colleague, and her colleagues that is now under review, showing some work they're doing on understanding of tornadic risks. And they showed what that's called a deterministic, on the left here, a deterministic prediction, where they give people a polygon and say, you're at that blue dot in the middle of it, how risky is it? And in that case, people are going to assume that if they're on the other side of that polygon, outside that line, they're not at risk, whereas if they're inside the line, they are at risk. Whereas the probabilistic representation to the right shows a whole range of probabilities, and you can see that the person with the blue dot is in one of the lighter shades of red. So intuitively and intentionally in this presentation, also a lesser risk area. So they're going to assume they're probably at less risk than somebody in a darker area is the assumption. Still, we're binning, so it's important to think about what the effects of that binning is. Next, please. In the next few slides, I'm going to show a specific example of how people might evaluate a risk map of the kind that we're talking about. And some of you have talked about a couple of these features that really matter, for example, the cone of uncertainty. So evaluability, which determines what people are doing with the information, how they're understanding it, is based on their understanding of the situation and the context that they're in. Familiarity with the type of visualization you're using is going to drive people's preferences for whether or not they like a representation of uncertainty, for example, but also, as we mentioned, graphicacy, the format of the visualization or how the uncertainty is expressed, and also the characteristics of the underlying causal hazard, so the hurricane characteristics in this case. And those together are going to influence how people understand what is trying to be represented here in the cone of uncertainty, which is hurricane forecast track uncertainty. And this is in this case, this is for Hurricane Delta. Next. But when Hurricane Delta hit Louisiana in October 2020, people were still recovering from a very recent hurricane, Hurricane Laura, which was right before that. And you can see Hurricane Laura is shown on the left, and now we have Hurricane Delta here in the next one. So that interpreted how people understood the uncertainties around the track. Next. In another study from Lace Padilla and colleagues, she looked at what happened using eye tracking studies to see when people looked at the cone of uncertainty in a couple of different types of formats. So here's the on the bottom here is a heat map of where people were looking in that cone of uncertainty representation. And they used this is where they would look according to an algorithmic saliency calculation that's done by Itty and colleagues. But other work, and I'll show you in a second, has shown that this does verify that people actually do look at these kinds of places. So boundaries do lead people to conceptualize the data as categorical, and people sometimes will then interpret the area within the bounds as a spatial representation of something rather than an uncertainty representation. And this is something that Susan Jocelyn and colleagues have called the deterministic construal area. So something that is represented over a space, like the uncertainties around the track forecast, can be interpreted as actually a representation of the area that is at risk rather than the uncertainties. Next. Now, in this study, there actually was eye tracking, and you can see here that it follows the kind of track in the middle here that it was shown, that was calculated by the algorithm that Itty et al. came up with. That people are looking down the center line, but they're also looking at the legend, and we do see in some cases that they're focused on right in the middle of well, this is right in the middle of the center line, in the middle of the temporal extent as well. Next. Now, Padilla and colleagues also showed people an ensemble display, trying to see if this would get rid of this deterministic construal error and correct people's understanding. And what they saw here is that people viewing the ensemble display on the right here were more likely to report the display indicated that forecasters were less certain about the path of a hurricane over time compared to the cone in A in this experiment. So it did correct that. Next. Okay, so the other thing that they talk about is how are we presenting these areas. So we saw that we had boundaries around these and they were bent, and McCachran and colleagues experimentally tested visualizations of 9 types of uncertainty to examine the effects of these various visual attributes in maps in particular. So it's location, size, color, hue, grain, orientation, shape, arrangement, clarity and fuzziness, the resolution of those boundaries in the images, and transparency of the images. Next. So here is this pulled out so you can see a little bit more about what it is. And what they looked for here is the intuitiveness of the logic in representing the uncertainty. So here we have 3 different categories from certain to uncertain, and this is fuzziness here on the left. And so it's very high level of intuitiveness compared to something over here, which is the arrangement, for example, of where something is, or the opposite using the solid to represent uncertain, and the very fuzzy to represent certain was counterintuitive, so not at all intuitive. Next. So in their results, they found that fuzziness is highly intuitive as a way of representing general uncertainty, but color saturation, which they also expected to be effective, was not. It was much less effective. Color saturation was much less effective to represent the level of uncertainty in counter to their expectations. Next. If you want to learn more about these, here are the 2 papers that I suggest you start with. The Padilla et al. Have done quite a bit of work on uncertainty visualization in maps and otherwise. And here's a summary that they put together. And the paper by Vanderblas et al. Is a really valuable resource for summarizing the literature on communicating uncertainty. Next. Okay, so how do we communicate this type of information to users? Over to you, Chris.
All right, so bringing it all together, we've got to think about their uncertainty in communication and our user here. And so what do we do with this type of knowledge? We know how people are reacting to some of this uncertainty information. There's different strategies, pros and cons, and we have a lot of uncertainty, as we heard the rest of the day, in a lot of different parts of our development and in our models. And so what we want to do is focus in on an example from TAI4ES. So if you think back to yesterday, we have this FogNet model, right? So it was predicting coastal fog from the Texas A&M Corpus Christi group, the same one that did the sea turtle prediction. And we're interested in communicating a really specific type of uncertainty, which is going to be very relevant for this group, which is around kind of XAI. So how are we going to communicate XAI to people? And this is something we're trying to do. And in our upcoming data collection with forecasters with this model, this is one piece of information we're giving them. So this is kind of our first way to start to communicate some of these kind of challenging and more kind of abstract ideas probably for a user that are very technical in hopefully a concrete way. So what you'll see is we've outlined this slide of information where we talk about, instead of saying XAI, which is probably not a term that people understand for our end users, forecasters, likely, we're saying understanding what the AI ML guidance is using. So we're looking at essentially, we're presenting as essentially like a case study in a weird way, where developers are examining the locations and want to know what the model is pulling on and what it's actually using to make sense and to make these predictions. And so we have a description with this probably pretty familiar to a lot of you of contributing away from predictions and contributing towards predictions. You heard this in a lot of different examples. Like this is the same color gradient that we showed when we had Antonios's maps up. And so we provide this language, and we're hoping to see what it does for end users' understanding and perception of these different types of uncertainty or potential new techniques that developers are working on, and seeing what implications it has for their overall trustworthiness in the model. And so we're going to check in. I think we got enough time for this. The first slide, Slido question, is a little bit of a knowledge check to see how we're doing and see if you can pull out some information from this. So if we do survey 410 here, it's going to ask you some questions about essentially how to interpret this and see if it's an interpretable approach to explainability, being a little meta there. So give you some time to fill that out, and I'll stop sharing this. So what areas contribute the most to the hits? What areas lead the model astray? What areas contribute most to the accurate predictions? Give some time to click through that. All right, we got some results coming in. The hits, upper left corner, okay. Ooh, wow, popular, 80%. Lower left. Okay, great. So then you can see that there's a lot of information. It took a little bit longer than normal polls for us to do that, which it makes sense because this relates to a question in Slido. You have to figure out, what you're looking at. So you probably looked at the axes, as someone pointed out. There's probably a little bit of a kind of an F that you're making. You're looking around different points and understand you have to find the hits quadrant, and then you have to go back and understand what's being communicated in the legend there that's contribute towards is red. Darker means higher contribution. So everyone's doing that perfectly. Nice. All right, what's the next one look like? Leading the model astray. So this is a little bit more of a spread. So upper left corner, we see the same. Where is it getting astray? This is a little bit harder because you have to figure out what does it mean to be led astray. So is it an accurate prediction? No. So letting it astray would probably be the when you predicted something was going to happen and it didn't, right? So that would be you predicted a yes on the left, but then it didn't happen, so a false alarm, and we see that it is pretty dark there in the top left. So that's great. And then leading it astray is also if you said it was not going to happen, and then or if you said it was going to happen and it didn't, which would be misses in the bottom category, and it's the same top left corner. Yep. So a little trickier to figure out and walk through that information, but we still got there, barely the vast majority. So great job. You could read most accurate predictions. Okay, so you predicted something and it came true, which is also, see if people get that, a different phrasing and communication of the same point. Right, so accurate prediction, it's a hit, but it's also a correct reject. So you have a little bit more of a spread on that, which makes sense because the correct reject has a bottom, the bottom left corner technically, but then the hits is the top right. So great, you're kind of teasing out these nuances. This is awesome. So now you're familiar with this XAI output. You can see how maybe a forecaster would look through it. I'm going to switch over to the next one, the next question. And actually, I think we'll go to, so it should be 411. We'll put that one live. Survey question 411. Awesome. So then thinking about it, as a developer, what can you do with this information? Knowing about like, this is what your model is doing, and you need to communicate something to an end user. What do you do with it? What are you going to try to share with your end user here? Why is this important information? Why do they care about XAI? Why should they? We're leaving some of these big, heavy-hitting questions towards the end as we have the last 10 minutes of the summer school. So examine the data in the upper left corner to figure out what's going on there and why it's contributing to both false alarms. Yep, so it's hitting on the right idea. So it's telling you where the predictions are coming from. You know, so this is what features, the areas the features come from are most important for sure. If you reject, you have a reject, there's something in the top left corner in the image. You don't trust it. Dark red equals fog with high chance of correctness. Okay. All right. So thinking about, again, knowing what's the contributing areas are for sure. To evaluate AI/ML, okay. You try to reduce the false alarms, communicate with the end user about potential pitfalls. Exactly, right? So then you can see that blue section, you're like, hey, you know, we're looking at what areas of regions here are pointing towards these correct rejects, but it's also leading away from correct rejects. This is where it gets done astray. Use it to estimate uncertainty. Okay, for sure. So knowing where your feature is, like maybe there's uncertainty around some of your features for sure. Okay, adding percentages, important to predict the correct rare event. Yep, using the raw curve to gauge the model strength for sure. So this is maybe one piece of information that could be helpful compared to other pieces of information. So that's great. All right, so we got a lot of great ideas. I want to pause here because I want to make sure we have enough time for a send off. I'm going to skip the last poll, but I'm going to pass it over to kind of wrap things up here. And I believe Amy, that's you, is probably be a collective effort in some ways. Can we share a screen?
It is me. Yes, please share the screen.
All right.
All right. Well, we want to thank you for sticking with us for all 4 days. This has been great. I hope you have learned a lot about trustworthy AI for environmental sciences for weather and climate. We're keeping an eye on Slido, and so I will make sure that we're hitting any of the open questions, but I'm going to go all the way through the last few wrap-up slides. So go ahead and go to the next one. Oh, there were several more. There we go. Everything that we did will be on our website permanently, and I made these slides a couple days ago before the Zenodo discussion that's been happening in Slido happened. I will be getting everything on Zenodo, and was trying to do it today and have it published by the end of the slides, but it turns out it's not just click and publish. It'll be there by tomorrow, though, I think. And it'll have a link to all the notebooks and everything, and it'll also have a DOI because that was requested that people could cite everything. So we'll have the slides and everything. You'll be able to get there from our website and just click on education and you can find everything about the past courses. If you want to learn more about just us in general, AI4ES, what we're doing, watch us on Twitter, watch our webpage. We meet every other week in something we call a site-wide meeting. These are often open to the public. So if you're interested, the topics are always posted on our website. If you're interested in a particular one, you can email us on the contact us form and you could get, we can let you in. We don't publish the meet because we don't want it to be, Zoom bombed, but we'd be glad to have people in. And if you're interested in collaborating, if what you've learned from what we're doing is something that's exciting to you, then just make sure you reach out to the person that has been talking about that work, and we're happy to talk about collaboration. Next slide. I want to thank everybody. We had this slide on the very first day, and reminding everybody of everybody who talked. I want to thank everybody that contributed and spoke and everything, because I think that this was a group effort and it was truly a interdisciplinary collaborative effort. Next slide. And finally, thank all of our sponsors. NCAR, who's helping to run all the multimedia in the background and has been critically important. Google Cloud for getting all of us the cloud time. LEAP, which is an NSF STC, the NOAA Center for AI, and Radiant Earth, who hosted our data sets, and NSF, of course, for funding us. And I think that's the last slide. Okay, I did not want to forget this. It was not quite the last slide. Remember, if you did the Trustathon, there's going to be a fireside chat today at 3 p.m. Mountain Time. I'm in Eastern Time right now. So that's in 3 hours, right? Somebody can correct me in the Slack if I'm wrong, or in the chat. There's going to be a evaluation survey that will come out either today or tomorrow. We really, really, really would love your feedback. We used last year's feedback to improve this year. We also use the feedback in our annual evaluation with NSF. So yes, please do your survey when it comes. Don't just say yet another survey. Please fill it out. We appreciate it. If you participate in this Trustathon, you should have gotten an email from Tasia about how to join the fireside chat and do the Zoom. It will not be this same live stream. It will be a Zoom where everybody can get in and actually chat. Does anybody else want to come on camera and say anything else or tackle any of the other questions?
I just posted this in Slido, Amy, but we, in addition to the slides being available online, we tried to put together a little Google Doc with the code and a lot of references from today, since I know that was a lot of material kind of quickly. So I posted that link again in Slido. So go ahead if you want, if people want to follow up on anything we said today with additional resources, trying to make it easy for you guys to have something to refer back to in the future.
Yes, and I will get all of that put into the Zenodo.
And just one quick couple updates on the Trustathon. The blog post for today will be going live shortly. If you haven't had a chance to comment on the previous day's blogs, please go ahead and get your comments uploaded sometime today or tomorrow at the latest. They'll be open. The Jupyter Hub will keep open through next week if you want to continue experimenting, and all the code is on GitHub if you want to run it locally or in Google Colab. I want to thank all the participants who've helped, who've been a part of this week, as well as all the huge number of people who've put the notebooks together, answered questions, made updates throughout the week, made sure the experiences run really smoothly. So thank you very much. And if you're not able to join the kind of town hall at 3 o'clock, please leave comments in the Slack or email us or put in comments on the survey that'll be coming out. So thank you very much.
Okay, and before we sign off, we had everybody turn on their cameras so we can get a thank you to everybody who's been helping in the background. I think we've got almost all the cameras. Yes, please switch to grid. I don't know if that's what you're streaming or not. But thank you all. We have the multimedia team who turned on their cameras as well. They have been a huge help in the background. Y'all don't know how much is going on to make this live stream happen, and we appreciate it all. Thank you.
Yes, thank you so much. It was great.